All right. Oh, this other computer seems to have frozen. All right, let's try again.
Okay, I'm live. Sorry.
You're live, and I'm trying to turn mine on. I thought this was all going to be this amazing. Oh no, I've clicked the O live. Going live now, or is it live? Now I can see it's streaming. You're live. Okay, we're both live. Hello, everybody,
Hi.
and welcome to our very obscure and strange experiment in live simulcast, screen share, live stream, something.
And hopefully everyone can hear both of us on both streams, whoever happens to be watching wherever.
Right. Yes. So I have the chat up on a little monitor over here on my side, and so if you can hear us and hear both of us, importantly, because there was a lot of complexity involved in like the various capturing technologies to capture both the audio from the microphone and send it to Jason so that he can hear and record it and hear him.
Yeah, it's all way more complicated than it should be.
Thank you, everyone. Okay, I'm getting positive confirmation on my side, Jason. I don't know about you.
I am as well, yes. And someone said on my side here, wait, Matt? Which Matt? Oh, Matt Godbolt.
Oh, which Matt? What other Matts are there, honestly? It's such a common name. I mean, even before the website, I went by my last name because it's a pretty cool last name, and there are so many Matts. I don't know. Do you find many Jasons in general in your life?
When in the 80s in elementary school, there was no shortage of Jasons in any class.
Interesting.
As an adult, it is very rare for me to meet a Jason. I don't know where we all went.
Was there some great plague that took out only the Jasons? So interestingly, the first company I ever worked for was a company called Argonaut Games, and our founder was not a Jason, but he was a Jeremy, and his last name was San, and so his initials were J-San, and so we were J-San, or Jez-San, depending on how you pronounced it, and the Argonauts.
Oh, that's
which
awesome.
Made for a dreadful, and it took me probably 3 years of working there before I realized the pun. Could I make my own video a bit bigger? At the moment, unfortunately not. I think we're probably stuck with the technology for the screen share. Like, so I can see Jason. I'm being asked if I can make my own video a bit bigger.
You
I don't know
full
that I
screen
can.
on my side. I hit the full screen button on screen, and
all right. So if you want to see me, you should tune into Jason's stream, which is in the description. This is the weirdest thing. And moreover, this is the first time I've tried doing this where I have a second computer that's like showing me the stream so I can see the delay. And so now we've got, and at some point we can bring up each other's streams on each other's machines and get the slowest Hall of Mirrors effect ever known to mankind.
I say we avoid that. That seems...
It's like crossing the streams, is it?
Yes.
Quite literally. Oh! We've peaked. We've peaked too soon.
That's terrible. All right. Why are we here?
So anyway, why are we here? That's a very good question. Thank you for drinking out of a Compiler Explorer mug.
Oh, it's the only mug I use while streaming.
Oh, you're American. I've got one too. They're also available in the store. And of course, this is the perfect moment for the gardeners at the school opposite to start cutting the grass. So I'm sorry if you can hear any noise in the background. I have got this set up so that in theory the microphone is just very directional. Anything? No? All right. Well,
very vague.
Why are we here? So the reason I'm here is because you tweeted saying, "Hey, shall I do a live stream shall I try and convince Matt to do a live stream with me?" Yes. And that was probably the biggest tweet I've ever been involved in, or at least in recent times. And so then you and I spoke, and we tried to come up with something that we both loved, were interested in, thought that other people would be interested in too.
Right.
And we had this great idea of to us, talking about how emulators work. We've both written emulators. We're both children of a certain generation where we have a certain love of older, more emulatable hardware.
Theoretically simpler hardware.
Theoretically simpler. That's a very good point. Yes. And so we thought, hey, let's try and turn that into something that is interesting that we can talk about, right? I mean, you and I can talk about this forever. In fact, while we were brainstorming this, you made the very sort of prescient observation that we should have just been streaming our conversation about what we were going to talk about because it was more interesting than probably anything we've talked about thus far. So we're going to have to try and recapture that somehow.
So just for real quick, I am getting comments that I'm getting dropped frames and lagging on my side, which I can also see on my preview, but there's nothing that we can do about it. Nothing I can do about it. As long as the audio's fine, I think that's the most important part.
Right. Yeah, at the moment, so far, it seems like everything's okay. What software are you using? Oh, that's a good question. Yeah, we are trying out Screen.so as our video chat come screen control program. We experimented with this a little bit, and it seems to do everything we needed. It does seem to use all the CPU power in the world, and we're both on relatively underpowered machines. I mean, I say underpowered. It's a modern laptop, but compared to like a desktop, it's still lacking. So yeah, everyone on my side is saying that the audio seems fine, and on the side, stream seems okay. I'm seeing excellent connection over on my other machine.
I was just told that my audio is not loud enough, so I'm bumping my gain so everyone can see behind the curtain for just a moment there on this drive.
We're going to get to see what's going on. Oh, you're on your side.
Yeah.
I don't get to see it, though.
No, you didn't get to see it.
That's funny. Sorry. I should have your stream up as well. No, that would be too confusing. So anyway, emulators. Tell me about what emulators you have worked on.
What have I worked on?
Yeah, because I know that you've played around with them.
I actually, yes, and it just reminded me of, oh my goodness, I hadn't thought about this in decades. The very first emulator that I had any experience with at all. Now, for those of you who have listened to the podcast where I interview my cousin on CPPcast, he mentions that one of his hobbies, well, I force him to mention that one of his hobbies is writing an NES emulator on every new platform that he has the chance to, right? So the first emulator that I had any exposure to was one of his CNES emulators that I managed to get running on my Palm Tungsten E.
Whoa.
So it was attempting to run the emulator kernel actually in ARM mode because, for those of you who don't know the history of the Palm, it was originally a 68K Dragon Ball. Palm OS. I have one.
Have you got one? I love my Palm Pilot. You got it.
I don't know how easily I can find it. It's not worth the effort at the moment.
I
but
would
it's over there.
Just yeah.
So he wrote one of his NES emulators, and right. Sorry, backtrack. So the Palm was originally 68K Dragon Ball, and then the Palm Tungsten series or T series. It was an ARM core that emulated the M68K so it could run the old apps, right? So you could, though, call native ARM code. And so I was trying to figure out how to call the native ARM code and then spit it to the screen buffer. And I did get it working. I think it was probably like 1 frame per second or something, but I did get it running briefly. Yeah.
But there's just joy in doing it.
Oh yeah.
Emulating. So that was the first one. That must have been what, like late 90s?
No, that would have been after 2000s.
Okay.
It would have been, I think, while I was unemployed because I had time.
As is so often the case, right?
Yeah, 2002, 2003, something like that.
That's pretty cool. But then more recently, you've written an actual ARM emulator.
I have written an actual, well, yes. Mostly. It's like a Palm, you're more familiar with the Palm history than I am. Does V4 sound right? Sorry.
To be honest, my ARM history sort of begins and ends in late 2000s when I sort of eventually went over to the Intel world. But yeah, my early ARMs, ARM 1, ARM 2, ARM 3 era, but then they changed the numbering or whatever. But it's a 32-bit.
It's a full 32-bit ARM, yeah, because the earlier ones were 32-bit, but they only had, a
26-bit program counter they used the bottom bits and the top bits of the program counter to store the flags. So the program counter was the flags and the program counter, which was super cool because it meant that pushing and popping the program counter to return also could, and there was a little like a change on the flags instruction. That's what that little caret is on the LDMIA with the R15 thing, is to say, and also apply the flags. Okay. Or you could choose not to. So you could choose to return the flags that you had, or you could choose to pop the caller's flags.
Okay.
But that was neat. Anyway, but then it made a big change when it was a neat trick to get the flags in the PC the same thing, but it meant that when they broke out into full 32-bit, suddenly all the code that relied on that had to be written differently. It wasn't a simple upgrade.
My basic goal was to go for the lowest common denominator, the simplest possible ARM that both Clang and GCC could still target. That's what I wanted to emulate so that I could write C++ code for my own emulator.
Got it. Which is what you do. And you have, I think there's a video, CPPCon video where you or multiple potentially, where you show the whole IDE, which is the compiler, the IDE, and the emulator all in like one.
Inspired by Compiler Explorer.
But yeah, product placement. I didn't tick the product placement thing in the YouTube thing. I don't know if it counts as product placement if it's your own. I think it's, yeah. So that's pretty cool. I mean, like the ARM is a beautiful instruction set. And you know, I think people are asking in the chat here, or asked earlier, you know, talking about the differences between simulators and emulators. And someone who's on my side has asked what the best PlayStation 3 emulator is, and I'm afraid I don't know. We're probably going to be talking about hardware 2 decades prior to anything of that kind of level. I mean, the stuff that I know most is Z80 6502, yeah. And the earlier ARMs, but and then more modern stuff is just Intel based, but I haven't really emulated it as a system. I know the chip.
Computer architecture, the things that I know the best is the Commodore 64 as far as the actual, but that's mostly book knowledge. And I guess I still have my visual aid from last night, which is this. Yay. I don't actually know much about the architecture. I know it's a 6502 core, but other than that.
It's pretty neat, actually. One of the videos that I linked last night talks a little bit about it. We can put a whole bunch. I'm going to take notes about things to put in the chat afterwards, or the description afterwards.
Oh yeah,
that's links smart. To. See, I'm trying to be clever here. It's not working.
I brought a notebook, but I haven't written anything in it yet.
And that is reverse emulating. Yeah, that's pretty neat. So people in the chat here are saying like the PS3 is super hard to emulate. So that is true, right? My experience of emulators, though, and I think this is going to get into the core. This will leg us a little bit into the simulator versus the emulator.
Go for it.
So a lot of the modern emulators are able to do functional emulation. That is, they actually can hook operating system, because modern consoles, for example, actually have a well-defined operating system with well-known locations, which is like, this is where the networking happens. You're discouraged from talking, or maybe even banned from talking directly to the hardware because of all the DRM potential implications and all the privacy implications of reading any arbitrary thing off, say, the hard disk of a system. So you are forced through a layer. And at that point, as a game programmer, you're not really allowed to take advantage of anything secret the other side of that. So as an emulator author, you can say, cool, if you jump to this instruction, we just go and fetch. We can just do native code to do, managing CPU states, or reading and writing network packets, and so you can do sort of functional emulation.
Is that fair to say? Is it fair to make a correlation to wine?
I think so.
Okay. With
the exception that you're also probably still simulating, or still emulating, I guess, really the CPU.
Okay.
So it's about, for me, the distinctions between simulation and emulation. It's a spectrum, and there's a gray area in between the two. On the very far extreme of simulation, you are literally doing electrical and transistor level simulation of what's going on inside the entirety of a system, which is extremely difficult and complicated and very slow to do.
Right.
On the far right-hand side, you've got something which is more like wine. Wine's a great example, where it's native instructions on most computers. I'm running Windows binaries on my Windows Linux. Sorry, I'm running Windows x86 binaries on my Linux laptop.
Right, which is also x86.
Which is also x86. And then I am calling, I'm hooking all of the operating system calls and doing a translation at that level, a very high level. But there's no sort of expectation that I will get the exact same results, because there was never really an expectation in the Win32 API that anything that you about how the results were achieved. The exact results were achieved. Like, open a window, you don't know how the window is going to be open or why the window to get a window handle back. And as long as it conforms to the API, there's a limited amount of observability about what you are allowed to assume.
Right.
And I think what is it's Hiram's law, right? Hiram's law sort of does apply here.
Is that any problem in computer science can be solved with another layer of abstraction?
No, Hiram's law is it runs counter to exactly what I've just said, which is the any significantly used API will have all of its unintentional side effects taken advantage of. And it's a much better example. Just go Google Hiram's law.
Yeah. That's absolutely.
But like
true,
right? But because of say something like a Windows install, or indeed even a PlayStation 3 or PlayStation 4 type era hardware, there's a limit to what you can rely on because things can change. Obviously, trivially between graphics cards on a PC, you can't make too many assumptions about the exact graphics card that someone has. So you can't, the API is the protection boundary between you and what the graphics card's actually going to do. So, hey, it rendered a texture. The implementation is everything else is implementation defined. So I'm incentivized not to rely on it in case the next graphics card does it slightly differently. As long as it achieves the goal of the API call, then we're golden.
Right.
And even with modern consoles, and maybe someone can correct me if it's been a while, but the boundaries are being put in place partly for reasons of, as I say, privacy and DRM and other aspects about modern consoles being a lot more like a PC. But also pragmatically, if a chip can be replaced with an equivalent, faster, better, cheaper chip in like a second revision of an Xbox, you look at like the Xbox and the Xbox One and the Xbox One HD and a whole bunch of things like that. The hardware changed behind the back. Not many games had to be updated because they used an API.
Right.
And that meant that they weren't relying on the minutia of everything that was happening. And therefore an emulator, a strict emulator, can take advantage.
I think this
is... basically PlayStation 4 to like PlayStation 4 Pro is what someone's saying in my chat here.
An important, in my opinion, I think it's important. The thing that changed from the console era to the PC era is this no longer, the 8-bit, the NES.
You're going to pick that back up again?
Right, I am, okay.
It's good. No, it's good. I've got to find something equivalent on my side.
With that device, like building off of what you just said, with that device, the programmers relied on knowing exactly when every single thing was going to happen. Right. And by the time we got to the IBM PC and the clone era, you could no longer rely on that. You didn't know what kind of CPU was going to be in there. Even if it was exactly the same megahertz, it might be an AMD clone of the Intel chip, and it's going to have slightly different timing.
Right. No, exactly. And I think, so I think probably the last piece of code that I'm familiar with that took advantage in the PC era is Quake, of like minutia of like knowing exactly how to lay out. Like the entire game was founded on the basis of knowing that a Pentium chip did divides in a particular way, and it had an A and B pipe and U and V pipe, and the instructions were written that way, and that made it run on a Pentium at the right speed. But an AMD clone may not have had the same thing. It may have worked fine, but but you're right. That's where it started. Whereas when I left the games industry, I had worked on like PlayStation 1 games and Dreamcast games, and there, the operating system was a library you linked against, and you just like arranged for your code to be at a particular place in memory, and it jumped to you, and you used the library to support you, but ultimately you could ignore it as well and just write directly to the hardware because it was that naked. And I had the manuals open in my lap mostly when I was working, and you could like go, oh, this it's going to do this. The API was the hardware description as opposed to an abstract thing.
Right.
And that means that, you could take advantage of things that were much more subtle and much more fine-grained. And then winding the clock back to like the 6502 era that you sort of were just talking about. Yeah, I mean, like that was the only way to get decent games back in the 80s was to take advantage of cycle level trickery to get the most out of a machine. At least after the first few years of games coming out, people got smarter and smarter, and it was the case that everyone's BBC Micro, everyone's Spectra, everyone's Commodore 64 was identical.
Yeah, and for people who aren't respective viewers who aren't very familiar with this era, it is fascinating to go and look at like the earliest NES games or the earliest Commodore games versus the latest ones. They are completely different in how much complexity they have.
Right. And in fact, I'm fortunate enough to be still involved with a bunch of people who are still writing demos and games for the BBC Micro, which came out in like '84. And we are still discovering new things about how the BBC worked and how the 6502 worked, and like it's bonkers to think that it can sustain 40 years of hard development, and people still go, hey, there's this trick where I noticed that this happens when you do this, so we can use that to make another, get another sprite on the screen, or get another, another color that you would ordinarily not get on the display, and that's kind of exciting and interesting, and that's what I think I love about emulation. I think everything about emulation harks back to that era which was what I grew up in. Obviously, I think that's the key to this.
We never leave the kids that we were. Actually, I just read a book by Bob Iger, the CEO of Disney, and he that's how he ends it. Is basically we never leave the kids, the children that we were, something like that.
Oh,
yeah.
I get tingles on my spine there. That's one of those like sort of sort of ASMR like moments of like, gosh, yeah, that is really, really deep. And so all the earliest BBC micro games, someone's saying about that. Yeah, so where am I? For those unaware, this is the emblem of the BBC micro.
Right. So we said on the one end is the clock cycle things, and on the other end, now as you've given these examples, what were you paying attention when Apple moved from the 68K to the PowerPC?
A little bit, and well, not so much then, but I have friends who told me stories of that era.
I believe that's the higher level that we're talking about. They make API call translations where they can, and do emulation where they have to. And I think that's what also Palm did with the ARM 68K to ARM move.
Right.
And then I think Dolphin, the Dolphin GameCube emulator.
Yes, that does high level.
It does high level everywhere it can, and CPU where it has to. Yeah.
And in the chat here, somebody has asked, Austin, in fact, hey, Austin, how would you classify something like the Xbox 360 emulator Xenia that JIT compiles PowerPC to x86 and then executes natively? That's even more blurry in the middle. It's like it's still emulating.
Yeah.
I mean, and also, a friend of mine has just finished and released a 6502 JIT-based computer. And I think probably, and I'm going to say this without a lot of confidence, but again, the fewer tricks that you can rely on in terms of cycle accuracy,
right?
The easier it is to write a JIT, because you can take a large gob of code, of native code, PowerPC code in this instance, and go like, I can just run this. I can transliterate it directly to native code, not have to do too much thinking about what else might be going on in the system, because things that can't be assumed to be contemporaneous, which we'll talk about, I'm sure, shortly.
Right.
So I can run like 100 or 200 or 300 or 1,000 emulated cycles and just convert the whole lot wholesale to equivalent x86 and then run it. Whereas when you're talking about the 8-bit era and the trickery that went on then, interrupts are coming in, and the sensitivity to where the interrupt arrives within a CPU cycle, like one instruction is executing takes 7 cycles, and if the interrupt happens on cycle 6, then one thing happens. If it happens on cycle 7, then a different thing happens.
Right.
Those are important for some levels of emulation, and that's much more on the simulation side of things. And also, you've also got things like self-modifying code, which is rampant in the 6502, because you didn't have enough, or it was less performant to use the indirection registers that allowed you to essentially have pointers. So the easiest way to have a pointer is to have an absolute address in your instruction and refer to that. And then when you need to move the pointer, you update the instruction to point at a different place. But of course, if that's in the middle of your generated x86 code, it's not really a pointer anymore. You can't modify that code. And so detecting even that every memory write you could do may potentially interact with hardware in some way. It may interact with the instruction stream that you're currently executing, or it may, have it may be something that the video chip is using currently to rasterize out the screen. That becomes a very difficult juggling act to do, and also get the performance out of a JIT. Now we've jumped a long way into the kind of like these foundational things. I mean, we just talked about JITs and stuff. We haven't really explained what they are relative to other things, or indeed how one would write an emulator in general.
How long do we have?
We've got as long as you and I have breath and
coffee
and coffee, water, and whatever else. So I guess, where do we want to start with this?
So the point though today is we're talking about the extreme low end, like the cycle accurate. That's what the theory is.
That was what the theory was. Yeah. And I mean, during the discussion that we had pre this this chat, we sort of talked about, well, why don't we just like take a gate level version of everything and just simulate the gate? So that would be like the absolute ideal case,
right?
I think. And that would, I think, be the best thing, all things considered. But so let's make it concrete about the 6502 for a little bit, because then I can actually talk with some confidence about some of the things that we're going to be talking about. So the 6502 has been decapped. That is, it's been dumped into some pretty horrible acids and had a small hole burnt in the top of the chip.
You have a 6502 sitting around, don't you? You always keep one on a keychain or something.
I've got a couple of them around, actually. Let me just... No, that's the wrong one. So this one's on a breadboard because I'm actually using it. So this is Ben Eater is doing a course on how to build your own 6502 base machine.
So you have to watch my stream right now if you want to see this full size.
Oh, that's true, yes. Or I have to move it right up like that. So anyway, it's just a whole bunch of breadboards and wires and things. And it runs a little game that I wrote. And it's not particularly exciting, but there's a 6502 on there. So it's got like a whole bunch of... But yeah, sorry, to make this concrete. Let's make sure I get the right chip so I'm not going to get shouted at by people who actually know better than me.
Is it the one that says 6502 on it?
It is, but it's hard to read. I have to get my son usually to read them for me because my eyesight's going. But yeah, this is a 6502, this giant thing here. But the actual chip is about this, is not even my fingernail size, somewhere in the middle. And I'm trying to look at the screen.
You're pretty close, yeah.
And so what you do is you either Dremel off down a millimeter or two, which is, I don't know, 4/8 of a groat if you're American. I don't know what that is. What's 2 millimeters? 1/128th of an inch.
I think we would just say 2 millimeters. Honestly.
2 millimeters, right? Also, and then you're going through the plastic layer on the top of the chip. You put some pretty horrendous acid on the top of it, and you burn through the plastic layer, and then you're left with actually seeing the die from the top.
Right.
On the top of that die is actually a layer of glass. I mean, layer is strong, right? It's like microns thick,
like actual silicon.
Yeah, silicon dioxide.
Yeah. Okay.
Glass. So and to get a better shot, you're going to use an even more horrendous acid called hydrofluoric acid that burns that off, and then you're left with like the contour and relief of the transistors underneath.
Uh-huh.
You put that under a metallurgical microscope, not a regular microscope, because a regular microscope shines light from the bottom through the specimen to you. Like if you ever do like biology or whatever,
right.
Your little slides. You need to shine light from the top and bounce it off up at you. And then you get to see what the die looks like. And at this era of microelectronics, the transistors are visible with a relatively inexpensive microscope. And you can't see what type of semiconductor material each part of the chip is made out of, but you can start to infer it because you know how the manufacturing process works.
Okay.
They're built up in layers and masked. And so the different depths of each of like the little towers, if you imagine looking top down, refract light slightly differently. So they're sort of tinted slightly different colors. And then you can sort of do almost like counting, like, okay, we know that there are N-doped and P-doped areas of the chip. We can infer where the N's and the P's are based on some of the outer connections and go, well, this must be ground, maybe this is the N or whatever. And I'm really not an expert at this, but effectively you can, with relatively straightforward rules and a bit of human intuition, work out where the transistors are and how they're connected to each other. And you can then build a cycle accurate emulator.
Right.
And like an electrically accurate emulator. Electrically accurate. And if you go to visual, yeah, go
on. That's the 6502. Like, how many layers of transistors deep do we have on a 6502?
Oh, single layer of transistors.
So on a modern CPU.
Oh, yeah. I don't know how it works. I really don't. I mean, like, so the methodology for like the NMOS 6502, which is the easiest one to understand, it's very power inefficient as a process and as a way of the transistors are being used. But it's straightforward, and I sort of understand it hand-wavingly enough to be able to like stare at something and go, I think I know what that is. I know that they moved to CMOS and then some other manufacturing something, and it gets more and more complicated. I don't know that they're layering transistors in the same way. I don't know how it works, but for the ones the dies that I'm seeing, it's all single layer of transistors with up to like there are NPN-P. Then there's polysilicon, and then there's a metal layer on top of that, which does all the connecting. So there's like all these different layers, and you have to sometimes infer whether things are connected or not, because obviously they can cross over and there can be a layer of glass separating them and all this kind of stuff. And so you kind of are looking for clues of like, oh, I think those two are touching.
You have the URL for that. You know what I'm talking about already.
There's a Visual 6502.
Yeah. If you can paste that URL, and then we can both bring it up, because I don't know how well it would stream at the moment for that level of detail.
Yes, that's a good question. Well, I think I'm going to just Google visual6502.org. In fact, it just completes visual6502.org. So I've gone to Visual 6502, and then on the left-hand side, there is a column of Visual Sims. Click the 6502, and then you should see a JavaScript version. That looks like a photograph of the 6502. If you've got it up, let me know when you're there.
It is loading.
Yeah, it takes a little while. So there's like 3,500 transistors, which is remarkably few.
Right.
If you think about it, this is a full 8-bit processor. And yeah, if you now click the start button on the top of like the hex dump,
right,
you can start to see it run. And I don't know how well that's going to come out in the video, because it's flickering around as it's actually running. And you can see the memory is changing, and there's a little yellow highlight showing you where the memory cell that's been written to. And there's an advanced view which it talks about, and in there you can actually see all of the internal state of it. So people have had to go into this and work out where on the chip like the A register is, and the program counter, and the X and the Y, and all those things.
Right.
So this is not, yeah, go on.
This is the result of that decapping exercise, right?
Correct. There's a decapping exercise, and then a hand and sort of slightly computer vision helped tracing of all the different layers, and then a bit of an inference about which layers must be what to make sense given the design. And then, yes, then a gate level simulator has written on the top of that. And it's amazing. It's only like a dozen lines of code, but it's incredibly, as you can imagine, sort of recursive. You know, you kind of iterate through and say, well, okay, if this transistor is on, then this amount of current comes from this part to this part. Okay, well, that's connected to another transistor. And of course, they're all connected to each other. So it's not like a DAG. It's, you know, cyclic by design. So you just have to keep running it over and over again until it settles into a state where it's not changing very much anymore, which is kind of what happens internally. Yeah, go on.
It looks like it's simulating on my side at a hertz of about 3.
Yes. there is a C implementation of this that is so-called optimized C, and it runs about, I think, a couple of hundred hertz, maybe a few hundred kilohertz, actually. I know it's not up to like full speed on a like 2012 computer as that was on the site. So this stuff is not cheap to do.
Right. And
this is why, if anyone's ever done like FPGA design, or if anyone's ever even done hardware like level design, this is why testing is done in a very different way from like software. You know, you and I write like regular code, and we're like, yeah, this is fine. We write a test, we run it a few times, we single step through the debugger. It's like, no, we don't have the luxury. If you're doing electrical simulation level of like, well, if I lay out my chip this way, will it work? It's a long process to simulate and see whether or not your design has unintentional side effects. And of course, it's also a product of how good your simulator is.
Right.
There's some great oral histories with the person who laid out the 6502, Bill Mensch. It's in the Computer History Museum. I could listen to him for hours. He just talks for like 2 hours. They're asking him questions, and just him describing the fact that essentially, as a pioneer in this era, he was developing like an intuition about what things would work and what things would not work, that was kind of transcending their ability to simulate and also like to receive wisdom of the time. It's like, well, I just think this works, and you know, trying it out. And ultimately this thing was laid out by a bunch of people crawling around on a giant piece of acetate, you know, like overhead projector from like school time, using marker pens, you know, Sharpies, to draw the layers. And then they would take a picture from a camera high up, and then they would shrink it down, shrink it down, and shrink it down, and that would make the mask. And it's just incredible to think that that's how this was done. Amazing.
It's like cavemen using stones and twigs to make
to
a
build
processor.
Isn't it just? Isn't it just? And Bill in the oral histories talks about like the simulators that he wrote and ran, which of course again is like, this bootstrapping of the entire chip fabrication process, where you rely on computers to help you build the next computer. Very much, like your Twigs building the first, wheel-based thing and then using that. But I mean, just to briefly, just to look at the die here, you can kind of see what's going on.
I had swapped back over to your face. Okay.
Yeah. Oh, my beautiful raiment. So you can see at the top there that large chunk with what looks like almost obvious ones and zeros, like they're little squares. That is part of the PLA, the programmable logic array. It's essentially a regular laid out set of well-known transistor types that form particular types of gates. And then you could just basically weld and say, yeah, this one and not this one, that one and not this other one. Yeah, this one, this one, this one. What's happening is from the left side and the right side, the current instruction that's been read is being fed in to all the wires across. And in fact, the complement of it as well. So you've got like 8 bits of the current instructions and 8 bits of the not of the current instruction, each of the bits of the instruction byte, that is. So you've read a byte that's the instruction.
Uh-huh.
And I think there's also a counter that says which cycle within that instruction you are in. So you've got like maybe something in the order of like 20 bits worth of actual incoming data, the 8 bits, the other 8 bits, and then which sub-cycle you're in.
Okay, so let's take a second just there. So
yes. I'm going to check over here to make sure I'm not saying bad things.
You probably
sorry, Adrian. I was going to say this, Adrian. You're right. It worked first time. The 6502 worked first time. They drew it out, and it was unheard of. Well, Bill Mensch's well known for being so good at this, but they laid it out. They turned it on. It just did what they were expecting. I mean, how often does that work? Yeah, but anyway, back to you, sir. You're going to make an observation about this.
Oh, I just wanted to make sure for the people who are listening in here. So you're saying each clock, we can draw clocks, right?
Oh, yeah. Can you draw clocks? Does it work? Oh, I can't see them on my screen, but you can do it on yours.
No. I have to draw on your face.
Oh, that's fine.
So if we've got our we've got our clock signal coming in. You can see that, right?
I can't, no, but let me
oh, you have to switch back to the screen.
Hang on, I can do this. I can. Oh, there, yeah, I can see it now. Yay, there you are.
Okay. Let's see if that'll stay up. Now, each one of these clocks ticks here is not an instruction executed, right? So what you're talking about, the sub-instructions, you're saying it might take 4 cycles to execute an instruction.
Correct.
So it pulls in the instruction, and then it's stepping through the things that need to happen inside that instruction.
Exactly. So an example, so modern processors now are pipelined, and so some of these things are happening simultaneously. But in the era of the 6502, pipelining was just starting to come in. In fact, there's a partial pipeline inside of it. But concretely, every cycle is an operation on the memory bus as far as the 6502 is concerned.
Okay.
So if you have an instruction that is 3 bytes long, and it maybe is load, the instruction is load A from an address. So there's a byte that says this is a load A with a memory address. There's 2 bytes following that are the 2 bytes, that are the bytes that make up the address of the memory you would like to load from. And then you actually have to do the operation of reading from the memory.
Okay.
So there's 4 times you have to go out to the bus. So on the 6502, that would be 4 cycles. There's the first 3 are actually just reading the damn instruction out of memory, and the 4th one is doing what it said. And I can't remember if that load A actually has a 5th one for that one to update the program counter, but I think it's done in parallel.
Sorry, I'm going to have to interrupt you for just a second.
Please.
Yeah, I'm getting some questions about my computer struggling to keep up on the stream here. I know my viewers are getting lag.
Okay.
I'm going to stop the simulation just to make sure I'm not using too many CPU cycles. So the screen share software that we're using, or the video chat software we're using, is using a lot of our processors here, at least on my end. And I think that's my main problem. Someone says they're experiencing 0.2 FPS for me.
Oh my gosh. Is there any way, can you dynamically adjust the threads or maybe if you, yeah.
Let me see. I can't.
You can like say, hey, lower priority, please. Nice it. And Richard's just confirmed. Thank you, Richard, that it is 4 cycles for an LDA. I was doubting myself because because suddenly whenever you talk about something out loud, you externalize some of the internal thought processes and you go, is that true? Have I just made that up?
You probably made it up.
I probably did, yeah.
All right, I'm going to see if I can, you said reduce the priority of...
I don't know if that's going to help particularly, but, we can don't doubt the God. Oh, God, please, no, do definitely doubt me.
So it's Screen and OBS Studio both fighting for my CPU's attention. I'm at 90% without Firefox even doing anything.
Oh, heck.
And I don't think that I can adjust live the bit rate at the moment. So
let's have a look.
I think unfortunately...
I have a load average of 9.2, which is, given that I have 4 CPUs, really, 8 CPUs with crazy hyperthreading, I'm not in a much better position.
Right, okay. Yeah, sorry, there's not much I don't think I can do about it. Hopefully the stream will catch up a little bit here with
I was actually looking at whether or not someone's mentioned here having a second machine. I mean, we both have second machines, but like there's like little USB HDMI capture cards you can get. Yeah, and they're a few $100, so it's not exactly a small thing. But I did wonder about that, so that I can actually have a computer passively involved in the whole thing that isn't going to break and also take the stream down. So that's something else. Someone's saying, is the Game Boy is a modified 6502? My understanding is the Game Boy is a modified Z80.
Yeah, Game Boy Z80, yeah.
The modifications included like load and increment instructions for like load A with HL plus, where it auto increments HL at the same time, which is just a kind of a neat and cheap trick for something you want to do quite often.
Right.
Yeah. So they're all the thing. Oh yeah, someone said yes, and this is a modified 6502. Thanks, Inverse Phase, yay! I was talking about Inverse Phase last night, and he's in my stream. So thank you, Inverse Phase.
Okay, so the stream is getting better. I don't know if OBS is, sorry, people are asking questions about my OBS setup. I don't believe mine is able to use hardware because I'm running on an Intel graphics chipset laptop.
Right. All bets are off for me because I'm on an X1 Carbon on Linux, and that's supposed to work, but who knows?
Okay,
so I think going back to the cycle description and the picture that we had, just to round that off. So each of those sub-cycles, the way that the internal orchestration of the chip is done, so the fact that it knows that like on the, for having read a load A instruction, the next thing it has to do is read 2 more bytes and then put them into some internal store to like accumulate a 16-bit address. And then on the last one, it has to emit that address onto the address bus and take the result of that and put it into the A register. You can imagine that there are lots of taps inside the circuitry, like in the middle part there, or the sort of the top, the second third down. That's where a lot of the logic is going on. And what's happening is that top set is orchestrating and saying, okay, on cycle 4 of a load A instruction, we must put the accumulator into read from the internal bus mode. So at that point, whatever happens in that cycle, the accumulator will read and latch whatever happens to be on the internal bus. Simultaneously, it will have emitted the 16-bit internal register to the outside pins. So the address has been advertised on the RAM bus.
Okay.
It would have said, I'd like to read, please, rather than write. And then as a result, the RAM chip will have been pushing into the data bus, whatever's at the address that you had decoded. And the data bus obviously is also connected to is then connected to the internal bus. So the accumulator picks up whatever value was read from memory. And so you can see that, effectively your state machine that you would have written as a programmer would be like, in case 0, in cycle 0, I want to read a byte. Case 1, I want to read a byte, case 0, I want to read a byte and put it into the instruction register, which is like a special register that holds that.
We don't have access to that.
We don't have access to that. No, exactly. Step 1, having looked at that instruction register, we now energize these parts of the chip. Okay, we're going to read a byte and we're going to put it into the low address register. We then move to the next step. We're now going to read another byte and we're going to put it in the high address register. And then in the fourth step, we're going to say, actually, no, we're not going to read and write from where the program counter is right now. We're now going to read and write from where the address register is, and we're going to put that into the A register. And then we move on to the next cycle. Obviously, the next cycle is read the next byte of program memory and then dispatch effectively on what instruction you just read, and so on and so forth.
Is every instruction on the 6502 4 cycles?
No.
Okay.
No, in fact,
I didn't think so.
They are. One of the flag, like effectively the microcode. This is not really microcoding in the same sense that like an Intel chip is microcoded. This is more lower level, I guess, than that. It's more like just which areas of the chip are energized or not. The last step of every instruction is and read into the instruction register the next instruction and set my internal cycle to 0 again, so that I start at the beginning of the next instruction. And so that can happen at any point along the pipeline. So most instructions are 2 or 3 cycles. There are some 1 cycle instructions as well, although there's some interesting things that were discovered only last night. It was amazing. Yes, I was on a Slack thread. So there's a CMOS variant of the 6502, which was a slightly more modern version of it. And some of the internal instructions that were undefined, undefined behavior, which we'll come back to in a second because it ties into that PLA at the top.
Right.
On this version of the 6502 were then just defined, and most of them were just defined to be NOPs. Some of them were useful, and so they were actually used as we'll actually canonify this with a real name. This is a store 0. That became an instruction. That's a useful thing to have. Push X and push Y, those kinds of things. Other things were just said, no, well, rather than it being undefined, we're just going to say it's a NOP. And those NOPs just take different amounts of time because of the internal workings. And what was discovered yesterday was that the 1 cycle NOP, or some of the 1 cycle NOPs, NOP is no operation, inverse phase is saying that. That's like a do nothing. It's an instruction, which is useful for timing in some cases, or other times just because it falls naturally out of the design. But the part of the process where those PLAs tell the chip, various parts of the chip to energize, one of them is to check to see if an interrupt happened, right? So just before you fetch the next instruction, you say, well, wait a second, what if an interrupt's pending? Then I actually need to go and start doing the interrupt handling instead. Instead of the next instruction, I need to go to the interrupt handler. And
it doesn't interrupt at mid-instruction.
Correct. It doesn't interrupt at mid-instruction. There is a defined point at which it checks the interrupt thing.
Okay.
And that check is not present in the 1 cycle NOP because there isn't enough time for it to have clear or whatever, however it's done. So the observation was if you make a stream of 1 cycle NOPs in a row, then interrupts aren't, it's as if you turned off interrupts. Now, it's totally useless to know that. But it's so surprising that, in 2020, somebody is coming up with what I believe to be a novel observation about a 40-year-old chip.
Well, you say it's useless to know that, but in 5 years, we'll probably see some new demo that now relies on.
Not even 5 years. I mean, so that 1 cycle NOP is super useful for a variety of things, particularly in the sort of raster chasing demos where you're trying to do things with exact and precise numbers of CPU cycles. That 1 cycle NOP is a great way of getting an infill and just taking the right amount of time. I don't know that anyone's going to take advantage of the fact that it blocks interrupts, because if you're at that level of fine-grained cycle precision, you've probably you have to have disabled interrupts, because otherwise all bets are off.
Right.
So it's fascinating. So it took me forever to understand how on earth NOP is actually useful. Yes, so that's a good point. It usually isn't. Is the answer there. So anyway, winding back the clock, I mentioned about the undefined behavior of a 6502. So there's obviously a number of, there's 256 possible instructions with an 8-bit instruction word.
Oh, wait, I got a comment here, interrupt masking. I don't think the 6502 was complicated enough to have interrupt masks, was it?
It only had a single disable interrupt or not. It had the interrupt disable flag. So which was the biggest source of confusion as a kid growing up, is that you would do SEI to set the interrupt disable flag. You're like, wait, so that turns off, SEI turns off interrupts and CLI turns them back on again. Okay, that's the opposite way around to the way that I would think. One of those wrong defaults that's fun. Yeah. We're not aware of that at all. So anyway, there are 256 possible opcodes, and all of them will be fed into that matrix of things that turn on the chip or not. And every one of those transistors is precious. There's only 3,500 of them, so that no one's going to spend a lot of time thinking too much about handling all the cases where actually this instruction was not defined. So like, for example, 03 hex doesn't map to any one instruction. There isn't one. So it doesn't do anything. But of course, the lines are live. So maybe some aspects of the CPU are active. Mm-hmm. More concretely, and if I can just, I'm going to remind, on my channel, I'm going to go over to here just because I'm going to remind myself which instruction it is. And I'm going to have to, I've got my slides here from a presentation I gave on this, and I'm running through, sorry.
By the way, reducing the size of your head seems to have greatly reduced my encoding overhead.
All right, okay, so here we are. So for example, hex 84 is the opcode for store Y. Hex 85 is store A. Hex 86 is store X.
Okay.
Hex 87.
So wait. There's 3 registers on the 6502.
The A, the X, and the Y.
That's all we've got.
Registers. That's all you got. The
and
accumulator is basic.
All 3 of them are 8-bit registers, even though it's got a 16-bit address bus. So this is leading back to what you were saying before about writing, the high bit, then the high byte and the low byte and whatever to the address bus before doing the next operation.
Right. That's correct. So yeah, we've got 8-bit registers. So we have an A, X, and Y. There is an S register as well, which is the stack pointer, but it's very special as opposed to the. I mean, they're all special in the 6502 because the A is the only one you can do anything useful with. The X and the Y are indexing the offset registers. So yes, we've got these instructions, 84, 85, 86, and 87. And I've got the bit representation, the binary bit representation up on my side of things here. And you can see that basically they're only differing in the bottom 2 bits. So you could see that the bottom 6 bits probably index into the same block of areas of the chip that are going to be woken up, right? So like if the store operation needs these things on cycle 0, these things on cycle 1, and these things on cycle 2, then it's probably only going to look at those top 6 bits, or even a subset of those top 6 bits, to say this must be a store operation. So those bits of the chip wake up. Then the parts of the chip that select either the A register, the X register, or the Y register to push them onto the internal data bus, ready to go out for the store, are just looking at the bottom 2 bits. Makes sense, right?
Okay.
So if both of those bits are clear, the Y register is pushed onto the internal is just presented to the internal bus. If the bottom bit is set, but the top bit is not, of those 2 bits, then the A register is there. If the top bit and the bottom bit is not, the X register is. But what if both bits are set? Mm-hmm. Well, obviously, as a good C++ programmer, we would have a default that does something, or we'd do all of our possible cases. But of course, they didn't bother, understandably.
Well, you don't want to waste the space in the chip.
Correct. So the Y register is presented only if both are 0. But it turns out that the A and the X registers only look at their individual bit. So the A register only looks at the bottom bit, and if it's true, it presents itself to the bus. And the X register only looks at its bit and presents it to the bus. So if you put both bits on hex 87, then both the A and the X are both fighting on the bus. Okay. They're both presenting themselves to the bus. Now, because of the way that the NMOS technology works, the zeros win out. So if there's a 1 bit being pushed on by the A in one of the positions and a 0 bit being pushed on by the 0 wins. It grounds, basically, and can consume the current. It's one of those things I think one realizes is that thinking of these as voltage levels of being 1 and 0 is not really what's happening inside. It's really current flows that are happening. And so your ability, a 0 bit is not just a 0 volts. It's the ability to sink current and absorb the current that someone else who has a 1 maybe has. So what really happens in that hex 87 is the result of logically ANDing the A and the X register is stored out to memory. So it's well defined. I mean, as much it will happen every time. It's not like weird undefined behavior or implementation defined. This is what will happen. It's a necessary side effect of the way that the chip was built.
You said hex 87?
Yes.
I'm just
it's sometimes
pulling up the undocumented.
SAX is usually written.
87. There we go.
The SAX?
AAX is SAX or AAX, is the so and the X register with the accumulator and store the result in memory. And
that's why. And there's a number of these, and some of them are useful and some of them are not useful. And what of course happened is, way back earlier in this conversation, we were saying that game writers at the time would, of course, rely on the fact that everyone had exactly the same chip inside of their computer, and they could rely on that. And so they would discover this, and somehow they would torture that into being useful. And in my case, this was used in the game Zalaga, which was. And the reason I discovered this is, as a kid, my friend and I, we had the BBC Master, which was like the 128-bit upgraded version of the BBC, and they did change the chip from the NMOS chip to the CMOS chip. So they kind of that sort of implied invariant of like, well, it's always the same CPU was broken, and some of the more cool games that we wanted to play as 15-year-olds wouldn't work, and we had to hack them, obviously, to actually then use the equivalent instructions, which meant they didn't necessarily work quite as well or whatever. But it was a lot of fun. So yeah, there's a lot of fun there. Oh, hang on. So Richard Bobbin, yes, pull down 2 resistors. Okay, so so you can. Some other people who know more about this are pining in my chat. So
you have more of the hardware people on your side, and I have more of the software people watching on my side over here.
Right, exactly. And some of my old games industry chums have come in to probably laugh at me for wild inaccuracies, as they're still in the games industry, and I left it, 15 years ago now.
Did you leave it because of these tricks that people play?
No, I missed them. I missed them dearly. Anyway, so yeah, I have a picture of the address bus and instruction decode and all sorts of things. Yeah, anyway, so just to sort of finish off the sort of schematic there, then, so that middle block is a lot of control stuff, and at the bottom, the sort of somewhat regular looking area of the chip is the various registers. So you can see that they have many things coming into them to select which register is
so like
is
the entire bottom half basically is the register set?
As far as I can see, yes, and some of the ALU. So in the picture that I've got here, which is stolen off of 6502's website, the Y register is a column on the far left-hand side of the picture, then the X, then the S register, and then the accumulator is sort of in the middle of all of that. And presumably the accumulator is so far away because all of the ALU operations like increment, decrement, subtract, negate, whatever, are probably nestled around it so that they can access it very easily and quickly. And there's probably a data bus somewhere in the middle of that. So
right,
it's all good fun. So anyway, winding back to emulating, I think we've probably explained or partially explained why maybe one has to model these things at a very, very high resolution, as in all of these apparently indistinguishable to the outside world effects of like, well, does the interrupt happen on the 6th cycle or the 5th cycle of the one instruction? Those things came to be relied on by people certainly in the games industry, more specifically in the protection systems, I'll be honest with you. You know, that's the kind of thing where these evil things would come out, these timing-based attacks, because, of course, if you're trying to prevent your game from being cracked and copied or the code being disassembled, then you would want to make sure it's encrypted in a way that's hard to decrypt. And one way to do that is to use essentially a key to encrypt your code, which is time varying based on the hardware, knowing that as long as you can represent the key and you can encrypt using the timing, then it's very hard for someone to single step through and try and recover that, because time is passing and some of these things are actually changing in real time. Like an external clock chip is changing all of the time. There's nothing you can do about it. So if you're exclusive ORing with the time chip and I'm single stepping through it, that timing chip is still going. And now I'm suddenly, the key is changing under my feet as someone who's trying to break the system.
So I had a comment here say, what about chip synchronization with different clocks, like between the CPU and graphics unit? On the systems we're talking about, there's one clock, and these things operate two.
You could talk about your systems, and then I'll come back to ours. But yeah, go on.
So on the Commodore 64, there's one clock that is, it depends on what region you're in. And in TSC, it's 1.1 megahertz, and on PAL, it's 0.99 megahertz, something like that. And it's tied to the signal timing that's necessary for the output. Okay, that's the CPU. Yeah, you're right. So, okay, there's two clocks, I guess, but the clock is fed into the VIC-2 on the Commodore 64, and the VIC drives the 6502 processor. It has its own 2x divider. So I think that's right. Someone might correct me on that, but I think that's right. So regardless, the CPU runs at exactly 1/2 the speed of the VIC, but they are in lockstep with each other.
Right. So I think the Apple II, which uses 6502, the original ones, or someone's, again, I'm not good on Apple, so someone's going to correct me, but they had the similar kind of thing. It was 1 megahertz. And then there was like the CPU can run at faster speeds,
Right.
but because most of the peripherals ran at 1 megahertz or required a 1 megahertz signal, that it was clocked down effectively.
Right.
On the 6502, and I believe there was a daughter board you could get for the Apple IIe that did the same trick. What the BBC Micro did was clock the CPU at 2 megahertz,
Right.
but detect when it was accessing hardware. And when it did, put the brakes on, synchronize the 1 megahertz and 2 megahertz clocks, and then run the CPU at half speed during that bus transaction, and then speed it back up again afterwards.
Oh, wow. Okay.
Which was very cool because, of course, the vast majority of the time you are not talking to hardware and you want to actually get the full speed. It's worth noting as well, this is something we pointed out in our chat prior to this, this was the golden era of computing when the RAM was twice as fast as the computer because the video chip and the CPU both wanted access to the same banks of memory. And the way that it was achieved, certainly on the Beeb, was that you ran it at 4 megahertz and effectively every other cycle of the 4 megahertz was given to either the video chip or the CPU.
So
which is just crazy.
On the VIC, on the Commodore 64, since the VIC was driving the whole process, the VIC was also the RAM controller. It's running at 2 megahertz. And the memory only had to run at 2 megahertz. But the 6502 would access memory on the opposite clock
like
cycle.
Rising. Oh, okay.
And,
right.
They knew that it could only access it at half the speed. So there was, the VIC knew exactly when it was allowed to access the memory.
Right. But I mean, it's just bonkers nowadays with RAM being, 3 orders of magnitude slower than CPUs. It's hard to imagine a world in which the solution to a problem was like, run the RAM twice as fast and give it
only access on the down clock cycle. It'll be fine.
Yeah. Someone talking about DDR. I think DDR is maybe a similar. That's more about how the bus is pumping the RAM, I think. But I had to talk about that somewhere.
To know how that works.
Yeah, or it's Dance Dance Revolution is being pointed out, which is also true.
Oh yes, that I understand better.
Right. So so that was actually one of the more significant and interesting, and I believe novel aspects of my emulator. So I think we didn't talk about emulators. Here I am jabbering away about it, but I decided I wrote an emulator for a BBC Micro in JavaScript because that's the right language to write emulators in, obviously. And
did you get better than 3 hertz like this?
Yes. It run considerably better. So mine is very strictly an emulator, not a simulator. So simulators are much slower. We talked about that, and but they are sort of the holy grail. And even the C++ implementation of an emulator is super, super slow. I know that some emulator authors that I'm in contact with have used the C++ circuit level simulator, C, I should say, circuit level simulator, to cross-check their handwritten, more straightforward implementation of the CPU to make sure that they agree, which is a great way of using that resource. And then that to me is like the difference between simulation and emulation. So simulation is, as far as you can possibly tell, you are doing the lowest possible observable unit of I can't use the word simulate here. You're simulating at the lowest possible unit of resolution. In this instance, you can resolve individual transistor states. Right, that's the kind of level we're talking here. With the emulator, what you're trying to do is make it as if you're doing that.
Zero insertion force?
No, as if.
Oh, as if. I thought you said
as in the.
Sorry.
I'm trying to broadly keep us in like sort of C++ territory here. The as if rule for emulator is that if the software you're running can't tell it's being emulated and not actually simulated or running indeed on the actual hardware, then you're doing something right.
And this. Okay. Wait. First of all, your emulator, JSP.
Yes, sir.
What's the URL?
It is one of the few things that you can type in front of godbolt.org and not get to Compiler Explorer. So bbc.godbolt.org.
bbc.godbolt.org. And just to prove that you can go there and it'll boot up a BBC Micro emulator.
You might have to click in it to get the sound.
Nope, it just beeped for me right here.
Oh, it did. Excellent. All right. You've obviously been to it a couple of times before. Chrome has some weird... Oh, is it Firefox you're in?
It's Firefox, yeah.
So I was very pleased. So while I was writing this was, gosh, getting on 8 years ago now. It was my wife's mother's 70th birthday, and she took the kids back to England to go and see them. And I had a long weekend, and I started this project. And and yeah, very quickly, I got to a stage where I was suckered into it, because I've done emulators before. I've written a Sega Master System, which is an 8-bit Sega console emulator before this, and I worked on one way back in the mid-90s that was written in ARM assembly, because that's a sensible thing to write an emulator in also, in case you were wondering. Yeah, exactly. That was mostly a friend of mine, actually, who I was hoping might join us today, in the chat at least, but he did the lion's share of that emulator. And again, all in straight ARM assembly, mainly because you had to, just to get the performance. And then I rewrote that emulator in JavaScript many years later on, and that was my first foray into this. And then JSP came out of that sort of naturally. Again, the idea was proving to myself that JavaScript was too slow to do this, and it turns out it isn't. It's pretty cool. But I made some good friends on the Mozilla team of some of the people who are doing the core JIT compiler inside Firefox, and so I filed a whole bunch of bugs with them, and as a result I have some great swag from them. So I definitely wholeheartedly recommend, if you are ever finding issues that are really interesting, because these are fun problems, like most things are like, oh, the web page didn't load properly, or like the layout engine put something over here. But if you say, hey, if you run this thing, which is a whole computer emulator, it's reporting all of these weird de-optimization errors, I wonder if you can do something about it. Like, oh, that's fun. So right. And then you get a bunch of swag in the mail, which is great. So yeah. So anyway, that's my history with emulators of recent times. So JSB is there. You've got it up and running.
I do. I'm just impressed that it has lowercase letters.
Oh, you actually have to put everything in shout caps though in BASIC. So if you're going to do the inevitable 10 print JSON is called 20 go to 10, which I encourage you to do. Okay. You have to do it all in shout caps.
It is. That's weird. So, but, oh yeah, well, it automatically does it, huh?
Oh, it should be. The caps lock's probably on. Yeah, it boots up in caps lock mode, and it's got nothing to do with your actual caps lock.
Oh no, where's the quote key?
Oh, the quote key is Shift 2.
Shift 2. Okay. Oh, okay. Okay.
Yeah. So that's one of the more interesting things, right? If you're emulating a piece of hardware, if you were if you were like doing a very high level emulation of it, then what you would be doing is, of course, telling the emulator somebody press the quote key. Right. But that's not what's happening. What's really happening is there is a count up timer that's running inside the keyboard of the BBC Micro, and depending on which modes you've got the thing in, it's either strobing across all the lines of the keyboard, looking to see whether there's a connection between a column and a row, and then if it is, it may raise an interrupt, in which case it tells you this location of the keyboard is down. So you often get... Yeah, go on.
I'm sorry, how do I break?
Break? Escape.
Oh, okay. Thanks. All right, never mind, go ahead.
There you go. If you hold down Shift and hit F12, then let go of F. Yeah, just basically hold down Shift and then tap F12 and then let go of Shift. You can get that's disk boot, so it'll fire up something vaguely interesting. Yeah, exactly. So,
so my listeners are hearing the drive emulation sounds.
Well, of course, you have to have a drive, and it's very important. To me, that's like that is one of the more emotive things about it, is hearing that disk drive noise and the noises. And I don't know if anyone else has this. Sorry, someone's heckling me on my chat. I'm just amusing myself with the inverse faces thing. Yeah, for me, the most emotive thing is that disk drive noise. And today, like when I'm thinking about something or something's taking a long time, in my head, like when I'm waiting for my Windows PC or when my Linux machine to actually do something, I'm playing the disk drive noise of like, this is obviously taking a long time because it's seeking backwards and forwards. It's like, and you're like, oh no, it's taking forever. And
I listened to my Commodore 64 drive, the 1541, for so many hours, but that I don't have that.
I'm being laughed at by my family over there. Who are you watching it on there?
I did, and it's just like a 2 second gap.
He's telling me the delay by my son's watching on his phone. This is so weird. What a world we live in, hey? What an interesting world.
I just had someone say my ears are bleeding in response to the.
Oh, I'm so sorry. It is horrible, actually. It is a horrible noise. It's way too much.
But I don't get that emotion with the Commodore 64
okay.
for whatever reason. But I do with my best friend's dad had a PC. And with 2 floppy drives, because what the heck, right? 2 floppy drives in his PC.
Yeah.
And when you would power that thing on, the drives would do their post in order. So you'd hear every time we turn on the computer, and that's what's sticking in my head.
That's what's being said in my channel right now. The definitive old school PC boot noise is the beep floppy beep, which is more what you're describing.
Yeah.
Yeah. So if you really want to make people's ears bleed, and I don't propose that you do this, you can load up an audio tape. So obviously,
no, yeah. Do you actually hear the?
Oh, what's wrong with you? Of course you do. Why would I not emulate the sound of it? It
depends on.
I don't have to. I actually implement the damn thing to make the sounds of it loading, and it is the most high pitched whiny nonsense. But yeah,
it's like listening in on a modem phone call.
Yes, a very early modem phone call with a lot of high pitched. Yeah. So it's all good fun. Yeah. It's all good fun. Anyway, so simulation, emulation, I think we've sort of broadly skirted around those things. And certainly my experiences with writing JSB and getting things to run that I wanted to. So for example, you can be very, very, very inaccurate, and you can get the BBC Micro to start up in the state that you're seeing it now with the 10 print JSON call.
I've got Elite on here right now.
So. All right. So really interestingly, and you won't be able to see it on yours, but if you've got it to the scrolling, the 3D ship, which is coincidentally just an amazing feat. I'm going to rewind back to. I have a picture.
At least every now and then, not to be drawing the vector.
Right, that's just how it works. Actually, it's more about where the raster beam's being caught by. It's not synchronized with the full screen thing. But those, if looking at my channel here, and if I could paste to you in an easy way, I'd give you the web page now. But you can see that I deliberately, in my talk that I do about this, I deliberately scupper one of the things that has to go on inside the engine. I make it so that I don't synchronize and run the hardware in lockstep with itself.
Uh-huh.
So this would be the equivalent to saying emulate 100,000 cycles of the CPU, emulate 100,000 CPU cycles of some of the other peripherals, like the video chip, and then do this, and then show the results,
right.
And then go back and do the CPU, and there's audio in there as well. So you could imagine doing it this way. It's not a daft thing to do at all. Is to say, well, run the CPU for a bit, run the various hardware one at a time, and then you fall foul of what you're seeing now. If you've got it in the rotating ship, on your side, if you look down at the juncture between the black and white display of the rotating ship and the color display of the Elite, the bit at the bottom, I don't know if it's on that.
The map or whatever. Yeah.
Yes, there's either at the far left-hand side or far right-hand side. You're probably seeing a little flickery dot. Are you seeing that?
Down here in the bottom corner at the junction point. Yep.
Yeah.
Left-hand side. Yep.
What is happening there is the video circuitry is being switched between 2 different interpretations of what the screen is like. So in the top half, it is in a higher resolution, lower color mode.
Right.
And then the bottom bit, it's in a lower resolution, higher color. So it's the same number of bytes that are being read by the video circuitry every clock tick, but it's just interpreting them in a different way. In one case, it's generating more pixels for like but 2 color. And in the bottom half, it's doing more than one color, but it's having to consume more bits, and therefore the output pixels are wider and fatter. But that's not a native thing that the hardware supports. What's really happening is that an interrupt has been scheduled to happen just as the beam is leaving the right-hand side of the screen in the high resolution. Right. And while it's going off the screen and rewinding and coming back on the left-hand side, the video circuitry is being completely reprogrammed.
Right.
Such that by the time it sweeps back in again, now we're in a high color mode. Now, obviously, if you were emulating giant chunks of the CPU and then giant chunks of the video, you would miss that. There's no synchronization between those two things. Like the fact that you reconfigured the video circuitry over here doesn't take effect until you've gone over here, and then it's too late. So the example I have on my screen here is where I deliberately scupper that with a URL parameter, and you can see that it's far more exaggerated. Like the bit that some of it's in some color, some of it's in low color, and all that kind of stuff. So
I think you can paste in the chat window between the two of us. If
Oh, can I now? All right, I'm gonna see. All right, hang on a second. Yo, look at that. If I do that,
I don't know if I can. Yeah,
that will get you the same picture that I've got, and then I wonder if I can actually get the cheating URL. Yes, I can.
Let me click on it.
Oh, get out!
It pasted as a URL, but then it's in drawing mode when I'm over your face.
Oh,
when I try to click on it. Oh well.
Oh, hang on a second. I've got a new keyboard, and so doing shift break on my side is hard. Okay. Oh no, that didn't work.
Yeah, that's all right.
Welcome. Oh yeah, no, this is because I do a whole demo around it, and it's more complicated than that. Normally I practice these things, but this is obviously just me making things up as I go along.
Yeah.
Anyway, so one of the sort of interesting challenges as a programmer writing an emulator that's trying to be as faithful and accurate as possible. Oops, I'm trying not to draw all over your face, but I clicked on you. is that tension between the efficiency and the ease of writing the straightforward straight line code of, opcode equals read RAM brackets PC ++.
Right.
Switch opcode. All right. Case A9, which is load A, read through more bytes, do some stuff, update the A register, update the flags, and then continue back to the top of the loop, which does the switch again, right? And that's great, but it doesn't model time passing, and it doesn't model the fact that if you're writing from memory, that isn't always memory. It could actually be a hardware device that's changing under your feet, or it could be something which is also being read by the video circuitry. So if you change it, then you need to tell the video circuitry, which is exactly what we were just seeing there. So there's a tension between those two things. One solution is to pick a component in the system, which is like the primary driver of everything. Naturally, you would pick the CPU, and then you model time passing inside the CPU. And then at the end of each instruction, you just round robin everything else and say, oh, update as if this many cycles of time had passed. And that's a really good way of doing this, right? You say, okay, my load A immediate thing, I did my switch statement, I went in, I updated my flags and everything, I did the reads and the writes to memory. And at the end, time passed brackets 3 cycles passed. So now the video circuitry is told, hey, do 3 cycles worth of emulation now. The audio system is told, do 3 cycles worth of emulation. I have hey, William,
yeah.
Could you make me a cup of tea?
Yes.
Thank you.
Oat milk.
Slave
they
labor.
wanted to be on the live stream, huh?
Yeah, well, they have their own channel and everything, but this is all Minecraft all the time.
So that's how things are generally typically done. You say, I execute this instruction that took 3 cycles, move on to the next instruction.
Right. And of course, it gives primacy to the CPU, and that's probably the right thing to do in a lot of cases because it's the main thing. Now, that's how JSP was written for a long time. That's exactly, and most emulators are done that way. And again, depending on how accurate you want to be. Now, the real trick comes when you start modeling things that happen within an instruction, because essentially what we've done is we've got an atomic unit. The instruction is an atom. The instruction completes, and all of its accesses happen at some point inside there, like if it's reading from memory or whatever.
We pretend like they happened instantaneously, but that's not really what happened.
That's a perfect way of putting it. Thank you. So, in particular, the protection system by one Kevin Edwards for Ultimate Play the Game, who became Rare. They're a British company that used to make games for the Sinclair Spectrum, which was, I think, the Timex over in the States, and Commodores and whatever. This game here, Alien 8, was the bane of my childhood. We had a tape version of it, and we wanted to put it onto disc, because the we here is me and my friend Richard. And in order to take the tape version, which obviously takes forever to load, and put it onto disc, which is, we owned it, but we didn't always own it. Admission, this is what the admission is at the bottom of my screen here, is that we didn't always own the games that we did. I'm sorry, I'm better now. We've all learned, and I was a 14-year-old, so there's only so much blame.
I read a recent interview from someone who wrote disk cracking utilities for the Commodore back in the day. And he said he had never met anyone who bought the disk cracker.
Right.
Which
That makes perfect sense. We were discussing, so we've been disk formats have been a recent discussion for us, and like preserving the accuracy of disk formats. So full disclosure, JSB has a very functional emulation of the disk controller. It does not model it very well at all. It's very much like, well, okay, an idealized disk would look like this, and a bit of hackery to make the noises happen roughly in sync. But you could easily spend a whole bunch of time modeling the MFM and the FM encoding of the magnetic stripes in the disk on the surface of the disk, right? That's not what I'm doing. I have a byte of like, well, this is the byte that's on there, and I just poke the byte over and go, here's the byte. You wanted the next byte, it's the next byte, but you could actually make some use of that. And a friend of mine is doing some clever things with that. But yeah, the topic of disk copying utilities came up, and that exact thing came up as well. It's like it's like deliberately scuppered so that it wouldn't copy itself. And then other games would start going, well, if I put this byte here, it thinks it's the disk copier, so it stops copying my game. So funny.
Use disk copiers to copy disk copiers so you can copy the game that you wanted to copy.
Exactly. So anyway, this game eluded Richard and I trying to crack it because it used all the tricks of the decryption and encryption that we talked about earlier. It used all sorts of timers. It also had an interrupt handler which deliberately corrupted registers as they were happening. So like it would just increment the A register and then return without preserving the A register, and then it would schedule interrupts to happen such that was a useful side effect of what it was doing. So any kind of disturbance in the force at all between a logic probe or anything that could disturb the circuit would put the key off, and it would fail to decrypt. And of course, once it had decrypted, it just ran into the game, and then you were playing the game, which is great. But if you couldn't, there was no like debugging at that point. I couldn't breakpoint it because they would disable all of the abilities for you to do that. So the only way to play the game was to decrypt it and run it. And we wanted to go, no, decrypt it, stop. Now I want to save that memory block and onto disk, and now I can play my game off of a disk drive instead of loading off of damn tape for 5 minutes every time.
Right.
And we could never get this to work. We actually wrote a 6502 emulator in BBC Basic, the thing you were just typing in. Mm-hmm. We wrote one in Basic to try and emulate a 6502 and the hardware of a BBC Micro, so that we could sort of have a single stepper where we could control time, including all the timers and things, in order to decrypt the game
on the BBC Micro.
On the BBC Micro, but we never got there, and we later discovered quite why. There's just so many subtleties. Mm-hmm. Of course, it begs the question: how did Kevin actually encrypt his game? Right? Did he have prescient knowledge and deep knowledge of like how all the interrupts handle, and did he carefully work it out and to determine and go, this is okay, now I know what the key is and I know how it's going to be done. Right, now I can just master the copy and then send it off to the factory. No. So we thankfully he Richard guessed it and he confirmed this was true. He desoldered the ROM out of his BBC Micro, and he replaced the operating system power on routine that wiped RAM with one that didn't wipe RAM.
Okay.
The code at the end of the decrypt, it would do a CRC check on the remainder of the game, and if the CRC failed, it would jump to the power on, which wiped RAM.
Okay.
So that would be if you ever mucked up the CRC, if you ever failed to decrypt for whatever reason, it would just go beep and be back to the black screen at the beginning. On Kevin's machine, that hadn't wiped RAM, and he knew that the kind of encryption that he was doing formed a ring. Thank you, Isaac. Formed a ring where it would cycle. It's like a random number generator, a PRNG, where it had a cycle of around about 200 odd. So when he mastered the disk, he went through that process like a couple of hundred times until it finally passed. Each time he saved the resulting garbage blob and then used that in the next step. And eventually it cycled around 255. Thank you, Richard. I figured it probably was that, but I wasn't sure if it was one of those weird Galois field things where it's actually a prime number around that or something. But so 255 times. On the 256 decrypt, it actually succeeded. The CRC passed, of course, and then it went into the game. And he just kept the prior one to that. And that was what went onto the disk and got mastered in the factory. So he didn't even know how it worked. All he knew it was 100% reproducible. But we have to know how it worked. So anyway, I'm proud to say that 25 years later, I was able to hack Kevin's encryption by emulating it cycle perfectly. And the clincher for it was the interaction between that 2 megahertz timer and the 1 megahertz timer, which meant that whenever it was accessing the hardware, sometimes it had to have like a half a cycle to catch the two waveforms up, and then they would be in lockstep, and sometimes it didn't. So there's like an even and an odd thing, and modeling that and working out what happened was the real last sort of step. And there's somewhere that we've got an evil spreadsheet that shows all the possible permutations and combinations of that. And
so,
but it's sorry, I've realized I've just gone on a one. Go on.
No, not at all. When was that? Just out of curiosity, that you finally cracked this? Like you said, 25 years later, but what year was that?
Oh, I'm gonna have to find out. It would have been. Oh, my computer hasn't frozen. There's you, and there's my terminal. Beep, and git log. I'm sure I'm going to say alienate now decode. There you go. I knew that I would have put it in the commit statement. So this was 2014.
2014. That's in JSB that you got that working, or different
Yes.
Emulator? Okay.
Yeah, JSB. I got that one working, and yeah, my pal Rich TW there is mentioned as well.
So you just said cycle accurate though. Is JSB now? How is it accurate enough to do this?
When you say how is it doing this?
Yeah, how did you do it? Like, how did you implement this?
So the sort of the journey to get to this point started out with the obvious case statement with all of the things, me handwriting all the instructions.
Right.
Now, pretty quickly on, you notice that store A immediate, store A 0 page, store A immediate, comma X, store A immediate 8, comma Y, store A 0 page, comma X, store A, and you're like, hang on a second, this I'm bored of writing this code.
Right.
Plus, I have to have like a table to do like a disassembly view. So, it's useful to have a table somewhere that explains to a program what the instruction is and how it should be decoded, just to present it to the user, so that if you hit Control Home, it shows you the debugger. Which, incidentally, if you're ever writing an emulator, every moment you spend writing a decent debugger for it is well spent and pays itself back in spades. I'm sure you must have noticed this when you were doing your ARM emulator, right? Having all the hardware registers open and having everything available in front of you is just a boon.
Yeah, and I mean, well, anyone can go check that out. That's CPP Box is the name of the project on GitHub. With C++ Box, I have to say, it is a personal pet peeve when people say CPP and they mean C++, but I can't name the project C++ Box on GitHub. So,
wow.
Sorry.
Remind me of your podcast. What's your podcast?
I did not name the podcast.
You pleading the fifth on me.
Anyhow,
anyone who has not subscribed to CPP Cast should do so now, and also look at C++ Weekly on YouTube. I just make sure that you subscribe on my channel. My side of things, people listening to me should know that Jason does this kind of thing like every week relentlessly and has done for years, and it's an awesome resource. So you should check it out.
Episode 217, 18 is just, yeah.
You just went live this morning, right?
No, the CBP Cast is this morning.
Oh,
that's episode 237. Yeah.
Oh gosh.
They're starting to catch, yeah. All right, so.
Yeah, but how do we get to... So I had a whole bunch of tables that drove the disassembly view. And so I then started to actually derive the code, which is, of course, something you can do easily in JavaScript. I can eval any string and turn it into code super usefully. So I started building from the disassembly tables the actual instructions. And then, so that had already begun. So like I see it's a store instruction, and therefore the only thing that differed in all of these things was the fact that, like, what is it I'm storing? Is it the A register? Is it the X register? Is it the Y register?
Right.
Okay. That gets put into a variable, and then the code that runs takes that variable. Brilliant. So it was a relatively straightforward thing to determine the rules about the instructions when various inter-cycle or intra-cycle reads and writes happen. So, for example, a store instruction, I know that the store is the last cycle of that instruction. For a rotate instruction, which is a read, modify, write. So there's an address. We read from that address. There is an internal cycle where it does the rotate. This is a shift, left shift, right shift kind of thing.
Right.
And then there's a cycle after that, which actually writes it back out again. That I know when the external access is, when the bus is active. I mean, it's always active for those playing along at home. There's a whole bunch of interesting side effects of that, which the talk goes into. But, I can work out when those things were. So just a relatively straightforward annotation and a few simple rules down all of the instructions allow me to say, okay, now I can my code generator that's generating these things can advance time rather than at the end of the instruction, but between the parts of the instruction where memory accesses that might be visible to the outside world happen. So, for example, I'm assuming that nobody is putting hardware peripherals where the stack is, right? That's seems reasonably straightforward. You could easily do that. I could build one right now. In fact, the one in my desk drawer here, I think actually the stack is potentially advertised to the some of the other hardware things. But but I'm assuming that's not going to happen. I'm assuming that if you do a push or a pop pull and it always writes to the same area of memory, it's like 1xx, then there's no hardware there. So I don't need to bother doing this kind of single stepping thing. But a strict simulation should do that, right? An actual full-on simulation should go, no, this is just like anything else. We should advance time one cycle at a time and let everyone have a chance to play. Similarly, during the read of an instruction, I'm assuming that the instruction pointer, the program counter, is not pointed at any memory that has any kind of side effect of reading. So I don't advance time cycle by cycle during the fetch of the instruction, which could be like 3 bytes long.
Okay.
And so with those sort of pragmatic things in, I've now got a list of like what happens on each cycle in like a bunch of an array, right? This is what happens on each cycle. And then there's a sort of optimization path that runs over and goes, which of these are observable? All right, this one's not observable. This one's not observable. Okay, actually just fast forward time at the end because nothing's observable in this instruction. So do all of these operations and then skip forward 7 cycles, say.
And you do that while processing each instruction?
No, it's done as a pre-process. So
okay.
It generates, it's effectively,
it's almost like it's jitting it.
It's like it's jitted, and of course, then ironically, that actually gets jitted. Not ironically, like the actual code that it emits gets jitted
because of the JavaScript.
Exactly,
right.
And there's a way. So you can't actually easily get the code for each instruction. You actually have to like fire up the emulator, and then like I've put like a hook in, so I can dump the text of each instruction, so that I can then look at it and go, oh, that's doing the right thing.
Is there a debugger that I can pull up as long as this is running in the background here?
Yes, press Control Home. I will do the same over here.
Control Home. Ooh.
Ah, the claw is our master. All right, where's my home key? There it is.
Oh, I can't move these windows around, can I?
No, come on. There's only so. This is an early-ish day thing. So yeah, you can see that there's a memory viewer there. You can flick through. There is you can name some of these things. If I remember rightly, I've forgotten how I've done this now. Oh, maybe not. That was my Sega emulator.
How do I make it go?
Oh, G to go again.
Oh, so I can't.
But if you want to N to single step, and if you can see, sometimes the screen is blank, sometimes it isn't. If you're pressing N, that's the single instruction, you may notice there's a funny dot on the screen. That is where the electron beam is right now, which is very useful for debugging things. So as you hit N, you'll sometimes see it working for you.
I don't see it, but
it may be off screen right now.
Dusty too, so.
All right, no, it's big. It should be big enough and obvious enough. But you can see all the hardware devices and all the other things that are going on in there. And really, the real debugger comes from when you can set breakpoints with like clicking in the margin, just like in an IDE. But there's a JavaScript thing debugger, so I can not debug it. CPU.
Well, I can click on a memory address, and it'll take me to that memory address.
Yeah, hyperlinks and everything. So yeah, there's a way of you can basically put there's like a listener style interface to instruction decode, to memory accesses and stuff. And if I could remember, there's the wiki somewhere tells you how to do this stuff, and I can't remember off the top of my head, nor will I bore everyone while I try and type it out. But you can essentially set a debug hook, and for example, get a histogram of what instructions are being run. Okay. Which is pretty cool. Right. Just by like going, oh, there we go. Or you can print out, or you can return true, and it'll like breakpoints. So you can have like the world's most complicated conditional breakpoint. You can also put it in a mode where it has a ring buffer of the last 256 things it did, and what the A, the X, the Y, and the address register were in each of those. So you can kind of like debug backwards. Which again, when you're trying to work out why someone's code isn't working, mainly because your emulator isn't working, right? You need to be able to go back and kind of go, well, what the hell's happening? And it's just really hard to do. So this is a lot of fun. And it's a huge time sink. But the cool thing about it, of course, is that, once you've got it working to any level at all, a whole world opens up. You've got all these games you can try. You've got all these like old memories of like, I used to type in, this in the video games, the shop where they used to sell the things, where you go into Matt is cool and then run away screaming, knowing that they couldn't stop it. Those kinds of things. So that's a lot of fun. And yeah, my miracle thing is somewhere else, which is the it's auto completing. Somewhere in here is the actual thing. Isn't it terrible? I can't remember my own URLs. No, that's the wrong one. Down it. Anyway, I have a Sega Master System emulator somewhere, which is not as advanced and definitely not as sophisticated in terms of its timing. And the interesting thing about that is because most Sega Master System games didn't rely on the tricks that BBC games used to use because it had hardware support for most of the things it cared about. It's like, you want to draw a sprite? Yeah, you put the sprite in the sprite table. There's only so many ways you can do that.
So what? Oops, I made you full screen accidentally.
Woo!
Well, I don't want to kill my stream.
I see.
The BBC Micro.
Yes, sir.
Used a relatively common graphics chip. I thought I saw. Yeah. No. What graphics chip did it use? It uses Texas Instruments chips for some of its stuff.
Yeah, we don't actually know that much. I would love to decap the 6845
really
CRTC and work out what's going on. We've done a whole bunch of really interesting like diagnostics on the chip. So a friend of mine's got an oscilloscope and we've put it through its paces to try to work out what it's doing. But we'd love to get a gate level understanding about what it's doing, which is another reason why going, as well as it being infeasibly slow to actually simulate at the gate level, a whole computer.
Right.
We don't have the chip diagrams for everything. And nor do we even know quite exactly how they work under some circumstances.
Yeah, the Wikipedia page for the BBC Micro doesn't even list what graphics chip it was.
I mean, there's two graphics chips. One of them's like an Intel CRTC, so cathode ray tube controller,
right.
And it's mainly generating all of the signals that cause the synchronization with the screen, and it's also generating the address for which the next thing happens. And then there's a ULA, which is like a sort of poor man's like bespoke chip that is responsible for taking the signals from that and then doing with the byte what you're supposed to do. So that's where the palette was stored, and that's where actually I think the cursor was generated by the CRTC as well. Yes, it was. So there's a bit of like wedging. There's a number of chips that are involved. There was also an SAA something teletext chip.
I see the teletext mentioned, yeah.
And so the teletext was essentially a character mapped display with control codes to change color and flashing and blinking and all that kind of stuff.
Yeah,
where the control codes themselves are, thank you, SAA 5050. I knew that someone would be there kicking my back.
The North American listeners here are not familiar with teletext, probably.
No, so this teletext was a real interesting thing in the UK, and I believe in some form across Europe, where during the flyback of a regular TV transmission, essentially there's garbage, right?
The flyback is literally when the electron beam is being repositioned to the top.
Correct. There's an amount of time off the bottom of the screen before it gets to the top to give the magnets that are in the electromagnets in time to wrench the electron beam back up to the top, so nothing's being displayed.
It again sounds like cavemen.
It is cavemen, right? It's wonderful.
The pixels out.
Oh, okay. Again, so thank you, Richard, for correcting me. I'm going to make vast generalizations, and then someone will tell me what the actual answer is here. So the first few off-screen scan lines, apparently, it's not during the flyback at all, but like literally just off the bottom, was an area of time when like there was an opportunity to transmit signal that wasn't displayed. And what would happen is that a number of bytes of information were being transmitted, and most televisions would be able to capture that. And what was happening essentially is, it's the top apparently, yes. I've got to love this stuff. Is most televisions would cache that, and in like a few bytes, I think it was like 1K of memory, they could store a page of useful information. And what would happen is that over a period of time, it was cycling through a number of pages, starting at like 100, 101, 102, 103, 104. And so our interaction with it was through the hyperlink of which page number it was. So the default, you turn on the thing, you press text, and now the TV picture would disappear. And instead you could be presented with this very low resolution, crappy teletext view of data that was being transmitted broadcast. and then you could go to page 101 or whatever, and obviously you could, so there was not really any navigation. You just had to look at which number it was. And it was a great way of having like TV listings, to having like magazine type information, and yes, subtitles. Yes, so one of the things would be like an invisible block, and so you go to page 888, and so the closed captions, to translate for my American friends, the subtitles were just teletext pages where most of the screen was see-through, and then you would have this little bit at the bottom where the writing came from the SAA equivalent chip.
It makes me wonder how that's broadcast in NTSC, if it's the same process or not. It's got to be.
I don't know that it is. They always seem higher resolution, the closed captions, whenever I've turned them on, like when I used to visit the US.
Okay. So my understanding is closed captioning on NTSC signal is the text, and it's up to the TV to render it.
Right. That's probably the same thing. I mean, that's broadly what we're talking about here. Essentially this whole page 888 would be updated with a screen full of information. It's just that most of it's see-through, so that you would see the TV picture behind, and then obviously where the writing would be where the speech would go.
Right.
And of course the broadcaster they weren't strictly serializing these pages out sequentially. They knew that 888 needs to update every time someone talks, so they quickly flip to 888 and say, okay, well, this is the new words for this particular part of the.
I got a comment from someone says, I am entirely too familiar with teletext from work.
Someone here has just said there's a music station which used to use that to transmit MP3. Holy cow, that's bonkers. So the only other thing I have on that kind of thing is that there was it's a quick origin story for the BBC Micro. BBC Micro, the BBC and BBC Micro is indeed the British Broadcasting Corporation, the TV state television provider in the UK. They wanted to have a TV program that espoused this new world of technology, and computers were going to be part of everyone's life. And someone had this prescient idea of well, why don't we make a TV show and then actually have a computer that goes alongside it, which is really pretty unprecedented. There aren't many other sort of fields of television where the television exec goes, you know what we need? We're going to talk about something, and we're going to actually sell the thing that goes alongside of it, especially in that.
Someone like ABC or NBC in the US at one time did Smell-O-Vision, where they would send you the scratch and sniff thing that you.
Right.
That's basically the same thing we're talking about.
Essentially the same thing. Pretty much. But so they put out to tender. They put out to tender with a bunch of technology companies. Hey, what would it look like? This is what we want the computer to be able to do. This is the price point. They went to Sinclair, who were making the Spectrum at the time. They went to, there's a brilliant documentary about this, and there's a kind of Micromen is what you should look. It's on YouTube. It shouldn't be, but it is. It's a sort of part documentary, part dramatization of what happened and the events around it. It's really fascinating, and it includes a whole bunch of people from Acorn who went off to found ARM. So some of my absolute coding heroes are amongst those, and it's wonderful to see. And all right, this is a complete self-indulgent moment here. As a 20-something, I had a couple of years where I was dating a pub landlady, and unbeknownst to me, the pub that I used to go and visit her at and sleep in, because pubs, you usually, if you're a publican, you live in the pub that you own.
That's a bar in America. No, I'm just...
So to translate for everyone else, no. So the inn where I used to go and visit her, unbeknownst to me, is a pub in Cambridge called the Baron of Beef, which turns out to be the place where there was a big fight between some of the people involved in both the BBC Micro and the Spectrum, the Acorn and Sinclair, where there was an altercation over why the contract was awarded to Acorn and not to Sinclair. And so it's a really, really interesting story, and I can't believe it. And so the dramatization is shot in the pub, and I'm sat there just with my mouth open going I used to live in there.
This is Micromen, right?
Micromen, yes.
Yeah, the people in my chat are chiming in with the actual title there.
Thank you.
So when we were just talking about the BBC, and I said it used a common graphics chip, which put us down this road, I had looked at the schematic with you last week. Well, not with you, but at the same time we were chatting, because we were discussing hardware, whether or not the bus can be shared, right? This was
That's right. Oh gosh,
Yeah.
yeah. Thank you for keeping us vaguely on track.
Yeah, so I was looking at the schematics and I saw a Texas Instrument chip that I'm like, I know this chip. So I just clarified my own confusion. And so this is to answer partially for my viewers who are looking at the web pages that I have up right now. The BBC Micro has the TMS 5220 speech synthesizer, which was very popular.
It was an add-on, I think.
Okay, well that's
But-
listed on the Wikipedia page. No, wait. Oh, that's optional. What did I see? Oh, the S. I saw some chip on your BBC Micro schematic that was a Texas Instruments chip, and it made me think of the TMS 9900 or one of the similar chips from Texas Instruments because they made a family of graphics chips that were designed for microcomputers.
Right.
That was my confusion on why I have these devices up on my side.
No, that makes sense. I mean, there's a lot of confusing parts out there and data sheets and things. Yeah, the TMS 5220 was standard on the USA Beeb, says Richard Broadhurst. So thank you.
Oh, so maybe that's the schematic that I happened to pull up.
And also, Richard also points out that there is a definitely not copyright infringing version of things. There's the actual people involved having interviews at the Cambridge Computer History Museum. So you can Google for Chris Curry or Steve Ferber. And also Steve Ferber. If anyone is watches a Computer File, the YouTube channel Computer File, Steve Ferber is sometimes interviewed on that as like a passing expert because he's now a professor at I can't remember which university he's at now, but he's brought in, and it's like he's one of the people who designed the ARM chip. It's just amazing to think that he's just some professor now. And yeah, when I did that, it's kind of cool.
It was the thing.
And yeah, no, it's awesome. Anyway, so sort of on track. Yeah, emulating is tricky, and so to do something cycle perfect was or cycle enough perfect to do what I'm doing. Took some compromises in both the way I wrote the code, some tricky tricks like table generating and code generating. And it occurred to me when we were first mooting this whole conversation topic.
Wait a second.
It occurred
before we get into the actual topic.
Oh no.
Is it okay to take like a 5-minute break right now?
Oh my God, I'm glad you asked because I'm busting for the loop.
Okay, I'm just going to step away because I don't want to mess up my stream by any chance by putting on my
Oh, your contract. Yeah, I thought about that. I haven't actually done one, so I'm gonna run and be gone for a minute or so.
Okay, we'll be right back then.
We'll be right back. And I will try and I'm going to put up as something. Oh, what am I going to put up? Oh, let's just.
It's a YouTube channel. Yeah. Yeah.
That's 6. 5, 6. 5, 6, 6. You want an end? Try to get one that was
Oh, that's interesting. I see here on my chat stream that yeah, sorry, I didn't know if you were going to be back. I was just chatting to my viewers. They someone commented,
and mine apparently as well.
the BBC uses the SN76489 sound chip, which is the same as the TI-99/4A. They share a sound chip in common.
There you go. And this will immediately pique Inverse Phase's interest in all of these things, which you should totally check out his stuff as well. He's a musician who uses old hardware, like harvested from old machines, you know, SID chips from the C64, other things that I'm sure he'll correct me in a second for in my chat stream, but like a whole bunch of them. And he builds like synthesizers and then performs live music, and both you know, covers and novel music. And yeah,
Inverse Phase has his own Wikipedia page.
He has his own Wikipedia page. Yes, he has an album that's on his Wikipedia page.
Wow.
Sorry, yeah, Pretty 8 Machine, which is everything. Everyone here who's listening to us right now should check out Pretty 8 Machine, which is a 8-bit cover of the seminal and awesome album Pretty Hate Machine by Nine Inch Nails, complete with amazing sounds, beautifully put together. And the best part, of course, the titles are all amazing hardware puns. So here we are, you know, head like IO instead of head like a hole.
And do not play it on our streams or we will be instantly demonetized here. So.
No, it's quite all right. But everyone should go to Bandcamp or Google Inverse Phase. Yes, Bandcamp. Yes, thank you.
Someone just asked if your TV is sticking out of your closet, and I would say no, that is an entertainment center. It's just not one that was necessarily designed for a TV of that width.
Correct. Yes, we used to have a TV that fitted in there, and then things, it doesn't fit. And then the world changed, and we ended up with a spare television, like you do. Like that's a thing that can happen, apparently.
In my neighborhood, many of the houses were actually built with drywall boxing out a TV spot.
Oh, yeah.
Which, within like 5 years, became out of date. It was terrible.
Get you back on full screen glory. There you are, beautiful. So, altogether more comfortable now. Yes.
Someone said your TV looks safe and secure. It is fine. It is sitting on a tray. I'm sure it's fine.
It is on a big tray. Yeah, this tray thing pulls out and can angle. It does. It's meant to push all the way back in. I have this pretty. Oh, my cable's not long enough down it.
Your kids are not young enough that you have to worry about them pulling down the TV.
No, quite. And you can't see it, but hiding behind the piles of Beyblades and things is like an original Xbox, and there's a Dreamcast up on the shelf. It's possibly just
I see the Dreamcast actually. Yeah, the distinctive 4 ports on the front there. Yep.
Yeah.
Yeah.
Isn't that cool? So, it's sad and dispiriting to me that when I go into a retro computing like area of a shop and look through all the old games that I'm interested in, I will find the newest game I worked on is now retro and has been retro for probably 5 years. So it's quite sad. Yeah.
Oh, we just mentioned all these random chips, these sound chips, graphics processors, CPUs, whatever. A long time ago, one of the earliest CPP cast interviews that I did was talking about, what's that emulation system?
Oh, the retro something. Hang on.
No.
This thing? The Retron 5?
No. This is a CPP. No, it wasn't that. It was software.
Sorry, I couldn't hear you then.
Sorry,
okay. MAME.
It was about MAME. Yes, there we go. So in the MAME episode, it was Miodrag Milanovic. we discussed the fact that MAME actually has implementations of each of these chips. So if there's a new system that they want to emulate, they basically just plug them together in software, and here's a new system.
Yeah. I mean, it's awesome like that. But it's interesting to think, like, there is an obvious like API of the chip, which is like, well, here's the clock signal coming in, so tick, 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 and then here are the pins, and I can plug a RAM chip in, and the RAM chip obviously does the obvious thing. And that would allow you to very quickly connect these things. I haven't looked at MAME. I'd be interested to see how it does it. But of course, you're back into this sort of more simulation, inefficient, inverted commas, way, and also harder to code. So I think, if we come back around to actually talking about typey types, then you'll see that like it's convenient to be able to write relatively straight line code that says case hex A9, processor.a equals read byte, processor.set flags, continue.
Right.
And you're like, that's my A instruction done. Okay, and I'm going to do all the other ones on my load instruction or whatever. And as soon as you have to break it down into, well, no, actually, because these things are observable, now I have to write a dreadful state machine, which is like case current instruction, then switch on sub-cycle, case 0. This is me reading the instruction byte. Case 1. Okay, this is the second cycle. Now I'm going to do this thing. And each time you have to return back out, which means there's no local state or anything like that. And so you're writing a state machine like a CPU.
Right.
And the poor compiler is going to have a devil of a time doing anything efficient with that. And it's just painful to write. Which is kind of where the idea of that there's a name for this kind of thing. If you need to do a piece of work and then sort of stop and then carry on at the next part.
I left my Knuth upstairs. I'm sorry.
So coroutines is what I'm talking about here.
Okay.
So a coroutine is essentially a way of suspending the execution of a function at a point and saying, come back to me later on. And my first experience with something which looked even remotely like coroutines, before even the Knuths, because he talks about it, is cooperative threading. As in fact, someone's just saying that there. Yes, it's cooperative threading.
That's how Windows 3.1 worked.
Exactly. And it's how RISC OS worked as well, which is my first example of it, where you have multiple programs loaded in, and the way that they each get some time with the CPU is they do some work, and then they call a function in the operating system, which is like, and what should I do next? And of course, to your point of view, it just returns you saying, oh yeah, the user clicked on your window, or oh yeah, no, actually, we need you to repaint this bit of the screen. But at that point is the opportunity for the operating system to say, okay, you called a function, but really, I'm stopping you. I'm going to save all of your state now. I'm going to save your stack, and then I'm going to load in the state and the stack of another process, and I'm going to return from their call that they made to the operating system saying, please, what should I do next? Saying, oh yeah, you've got some spare time now. You can do some work, or, like WM idle, or, nothing to do. And so there's this illusion that you are writing a single threaded program, which just occasionally checks in to say, what now, interact with the user. But that point is the exact point where a thread hop happens. And it's a fun thing to do. You can actually sit down and write that kind of thing with a relatively straightforward. It might be an interesting thing to do in your emulator and CPP box, actually, to write like a multi-tenant system. I don't
yet have the save state instructions and implemented, that kind of thing, to make that easy.
But you don't really need it. You just need to do, you've got LDMIA, presumably an STMIA, store, push and pop.
Yes.
That's all you really need.
Yeah, should.
So you just have two stacks, and your like hypervisor, the operating system thing says, okay, load in all of the registers for program A, and then load in the stack pointer that they gave me with I preserved when they called the function which says switch, and then return. And I'm returning back to a different place. Now my stack's somewhere else, so I get actually return over to them, and it's as if their program continues. So there's some pretty cool things you can do with that. I mean, it's a pretty low level operation to do, and obviously describing to a C++ compiler that that's what's happened is, I mean, you should be okay because it's a function call boundary, and the compiler will only make assumptions about what it can make over, especially if you make it extern, right? You're like, hey, this thing is a library function, which could reasonably have done all these things, right? Could reasonably have changed all of your memory. But it's not even changing your memory. You'll get the same view of memory back that you started with. So it's a fun thing to do. I'd encourage anyone to do that kind of thing, just to get an idea about what cooperative multi-threading is doing. And to an extent, what what coroutines are doing, where you would instead of it having an operating system level thing, it's within your own program where you say, hey, call this function, and it's going to return me a value, and I can carry on with this value. But unbeknownst to me, that function actually is halfway done. And I can later on say, give me the next one, and it will continue from where it left off. And all of its variables, all of its state will be as if it was like a micro thread that was running. And so anyway, to wind back, this would be a perfect way to naturally write an emulator that was cycle perfect.
Right.
Because you can say, this is the point where time passed. And I'm still writing straight line code. I'm still saying now my load A is still like, read the A register. Time passes is what I would say. I'd say like await or yield to someone else. Let someone else have a go.
I have a co-yield here, or co-await in my chat window over here.
Right. Now await and yield are sort of their dual in the way that I've been thinking about them. And I've actually struggled. I shared with you, Jason, that I've sort of like tried a Python equivalent of this. And
so
the
at
yield
some point here, we're going to have to do the desktop sharing thing and see if it works all right.
Yeah, I think we're getting there. But it seemed like a natural thing to try and use. Now, and also, it's a C++20 feature if we're going to try and do this anything in C++. It's not very well understood by either you or me.
Nope.
I think it's fair to say, right? I don't want to cast
Nope, not at all.
It doesn't even seem to be very well fleshed out in either the standard spec or in the library. We found CPP Coro, the routine there.
Theoretically, it is fully spec'd out in the standard spec because
we're finished. We're done with 20-year shift, right? Yeah, as far as I can tell. Yeah. But the interesting thing, I think, is that for most uses of coroutines, people are thinking about it as a lightweight thread replacement,
right.
Like a green thread, so sometimes they're called, where you're doing file I/O or you're doing network I/O, and you don't really want to spin up thousands of actual operating system threads that will block when you call read.
Right.
What you want to do instead is like async await a read. And from your point of view, again, the code looks like you're writing stuff line by line. But what's really happening is that you say await the read, and actually your function returned at that point. And someone else was allowed to run that. Some event loop is running other people's codelets. And then when your read completed, the event loop notices this and goes, I better return to you, and runs back into the coroutine. The co-await kind of returns. And so it's always about things that are happening outside, exogenous. Like, so there's always time-based things. And so you'll see any of the like async await stuff is networking or file or, time. Whereas what we're really trying to do is like actually do coroutines, like two routines that are codependent on each other, ping-ponging backwards and forwards.
Right.
And that's what Knuth talks about in his section on code. And I forget the motivating example that he had for it.
So,
but yeah.
Is my face big enough on your side that if I draw on the screen, people can see it?
Oh, your face is the perfect size, my friend.
So
yes, it is. They will see. You can draw all over the screen. I'm going to actually
try to. Let's get back our clock signal.
Okay, I'm going to draw back your full size and excellent connection, it says.
Okay. So if I have this, and then we're talking about these 4 cycles is how long it takes to execute an instruction, where previously we would say, okay, whatever. Store A.
Yep.
Wow, that's terrible.
That works. You said what it was. We can see.
Yeah. So if store A takes 4 cycles, and before you would say in your code that's cycle perfect, you go, well, during cycle 2 is when this data was read from the bus, whatever, and then you kind of split this in half. What you're hypothesizing is that at the end of each of these, or at some point on each of these clock cycles, you yield control back to the other pieces of hardware where they implement, or they do 1 clock cycle, and then they yield back to you, and then back.
Exactly.
Okay.
That's exactly it. Thank you for that. That's a much clearer way of putting it. And of course, like we sort of said at the beginning with, you can do this with loads of state machines, loads of switch statements and things, but it's just laborious, error prone, and just and ugly. So we were positing where maybe this could be a better way of doing it.
I just got someone asking if we can start over. They're late to the stream.
Okay. Morning, Jason. How you doing?
Hey. No,
we forgot to ask that. That's the beginning of every CPP cast. Is Rob asking you how you doing, and you're like fine, and you talk about the next conference you're going to, which it's too soon.
Yeah. So no, I don't even talk about it now.
Oh, I'm sorry.
It's fine. Actually, it's kind of a relief to not be traveling for a while. And well, since you brought it up. But I do feel like I quit cold turkey because I had been traveling like to another country at least every other month for like 3 years.
Wow.
And then, bam,
nothing.
6 months I've been at home.
Wow.
That's really weird.
That is. I mean, it's we live, I guess, you know, for those watching in 4 years' time on having Googled some weird thing and got a YouTube link, we're in the middle of a strange crisis right now. But for everyone who's watching live, they know full well why we're all sat in our houses not doing anything else right now, and hence having time to think about, I don't know, some strange live stream that we do.
You know, before we get back to since we're already
distracted, off topic,
there was this tool, and I cannot for the life of me remember the name of it, although I think Google's getting me there, that there was back in the day. It's not coming up. Back in the day in the Windows 95, Windows 3 era, you were talking about how this was cooperative multitasking. Well, if none of the processes actually had any work to do, Windows was effectively in a busy loop. And that didn't matter until sometime in the Pentium era, when Intel started actually lowering power use states when you were not doing something. So there was a utility that you could run on Windows that would, if no other process was running, it would run and effectively consume 100% of the CPU, but with no ops, so that the processor would go into a
sleep state, a lower C state. Yeah, that's correct. I mean, there's so many weird like oddities like that have come through. I was only talking the other day with a friend about there was something called. I was never really into the PC world, but I know that there were some things that like this. It's either Stacker or some other thing where effectively the virtual memory unit was used, and instead of swapping out to disk, pages were compressed and stored somewhere or put somewhere else.
Yeah, Stacker.
And just to try and give you a bit more RAM. I don't know. Yeah, but that was that Stacker. Yeah.
Modern Windows has a memory compression routine that you can see sometimes come up in your.
Really?
I don't know what it's doing. I don't know if it's compressing, or if it's collating pages to
Right. I know. Yeah, like Linux has the huge page daemon, which runs around looking for contiguous blocks of 4K pages and go, hey, you've got 2 meg of this. So I'm just going to use one page to map for the whole lot.
Right.
And I know you can do deduplication as well. And I know that hypervisors, now we're going to get really into the weeds here, but hey, there's no reason why not. I know that some hypervisors do this as well, or did do this, so that like if you were running on Amazon and like you and the other 12 people that were tenanted on the same machine were all running the same Linux kernel, then the hypervisor ahead goes, hey, you know what everyone's got? Everyone's got the Linux kernel loaded in. We don't actually have to use 12 copies of the 100 meg of RAM that constitute the Linux kernel if each 4K page can be shared amongst each other. And that's like brilliant. Or like, hey, everyone's loading libSSL in. So let's, deduplicate it across, tenants, which was brilliant until someone went, you know what we can do, though, is we can tell when someone else is using the same page as us, even if they're on a different machine, because we can look at how the cache responds to reading or writing from that memory. So I map in libSSL the same version as the tenant next to me, like a different computer as far as I'm concerned. And then I do some careful probing about how long it takes to read parts of the code of libSSL, and that allows me to infer whether or not that's run recently. Now, as long as I can get access to the other guy's implementation, like maybe they're a web server and they have an SSL certificate and I just keep making loads of requests to them, I can start to leak out which code paths are taken. And if you have a piece of cryptographic code for which the code path depends on, say, the key, you can start to leak bits of the key out. But it only works because it's the physical, actual same piece of memory that you're reading from as well.
So it's completely unrelated, but similar to the Spectre and Meltdown kind of things.
Yes, in a way. I mean, it uses cache timing as the side channel,
right?
But it doesn't use microarchitectural state,
right?
as the conduit by which it uses the fact that the operating system is deduplicating pages, and therefore you can sort of like infer what someone else is doing with what appears to be a different thing, but is actually the same thing.
Right. So did the hypervisors have to stop using that technique?
I believe so. Yeah. Now I'm very much out of my comfort zone. I know that it happened, and I read these security blogs. I'm like, oh, that's cool. And but yeah, not. I don't know that is.
CPU idler program called Rain. Sorry, I just got the feedback
You've
on
got
my
it.
channel here.
All right, we've got.
All right.
So someone's talking about RAM doublers here. So stacker, hardware cards. My son has got some head. Are you listening to anything in those? No. All right. He's just got my wireless headphones on for no reason.
I'm just mocking you.
He's mocking me apparently.
You seem to always have them on.
Put me in my place. What everyone needs is a 12-year-old, or not. So yeah, there were disk-based versions. I mean, obviously, virtual memory itself runs the disk, but the one I was thinking was like the RAM doubling technique of like compressing the RAM pages, and obviously then that got us onto this stuff. I'm trying to remember how we got here so that we can maybe wind back. This is actually something I've noticed, like with the crowd that we have on both sides, we're mostly logical, rational human beings that in the programming world, where we have built our sort of mental model over how like things work, and we can't help, I think, but model our mental processes on how computers work. So when I'm talking to you and we have a sequence of topics, and every now and then the topic changes temporarily, we model it as a stack in our heads, right? Naturally, we even talk about popping the stack, meaning going back a level. And I wonder if this is unique amongst software engineers, because other people call that a conversation, and they don't fret like I do about remembering what it was that we were just talking about. 3 layers, Stack Overflow is something that worries me, but other people are like, yeah, it's okay, we forgot about that. We just never mind. We never came back to it. So,
I'm losing frames from you, by the way. This is not on my side at this point.
Okay, all right, yeah. I must admit my offhand computer here is having some difficulty, so maybe we're starting to reach the point where all my neighbors are using their internet as well.
Okay. I don't think I have that problem here somehow.
Yeah, mine. I don't know that I do, but I have no other explanation. Maybe my kids are in the garden. I wonder if they were like pulling at the cable.
So if my viewers see choppy frames at the moment, I actually have an excellent stream. It's just so you know, not on my side at this point.
Yes, it says excellent connection over here, but it keeps giving the little spinny spin, telling me that like something's happening over there. But we'll see. Anywho, right. I guess, do we want to even attempt some code just to see if it even works? Or do we want to just keep chatting? I mean,
go ahead. I think you should share your desktop and show at least what your mock-up looks like.
Okay.
So when you do that, I'll go back into full screen for you.
I'm going to share screen. So click anywhere to select this screen so that I don't share the other screen. All right. Let me know what you can see.
I see your virtual 6502, visual 6502.
Oh, look at that. This is high tech. Right. So you and I discovered when I ran PyCharm before. Now, bear in mind, this is my poor computer trying to now load up a Java, significant Java program that's pretty complicated, while also decoding your stream and presenting it to me, and encoding my entire screen and sending it out.
And I'm just going to fake this. I put me over
the top of the thingamajigs down here. I have to remember that it's mirrored for me but not for you. People have already commented about that a couple of times.
Yes. There's an option whether or not we mirror. And just again, also for the sake of our listeners here, our viewers here, it's definitely going to prioritize your desktop over your video. I noticed that when we were testing this
we tested this out.
So
excellent.
Try to not do too much scrolling and try to keep the fonts big.
Yes. Well, I'm already in sort of Lego size, Duplo size font because of once I have my high resolution monitor kind of defaults to low res. So I'm going to try and find, there we go. All right. So how is that looking on your side? Is that
it is
viewable?
Viewable to me. I'm looking on my stream, and I think it is probably... Someone said, look at all those browser add-ons. I think they were referring to you.
Oh, gosh, yeah. Well, these up here, yeah, this is a bit over the top. Yeah, I need to fix that. I know, they're invisible to me. I never see them.
Oh, yeah, I see, okay.
All right, so I'm going to scroll to the very bottom of this and show.
So it does
like,
take a second for the compression to catch back up, but
catch up. So I let it like statically sit there.
Yeah, just let it sit for a second while you talk about it. Okay.
So what we discovered when we were doing this in test is that potentially PyCharm, or indeed any IntelliJ thing, is not going to listen to my key presses because of magic. So I'm going to just try pressing a key. Ah, it worked. Okay, this is going to work out a lot better than before. So in theory, Jason can take over as well, which is cool. You can draw pictures on my screen, and you can type. And this is screen.so, which seems to be doing pretty well. I mean, they seem pretty on the ball, despite the high CPU usage that we're both seeing. So this is the idea, and I did it in Python because rather sadly at the moment, this is something that I'm spending more time writing than I am C++, and I sort of understand how their coroutines work. And there's sort of two sides to it, as I understand. There's the generators. So a generator is a strict coroutine where you can get the next of a thing. It's like an iterator. Think of it as an iterable, except that every time you go to it, it is actually a program that continues running. And I'll show you an example of that in a second. Secondarily, there's sort of this async await, which is very much modeled over asynchronous processes where you implicitly become a sort of generatable thing and you're suspended at that point, but you're waiting for the result of another routine. And it's up to something else to schedule you and run you again at that point. So they're kind of dual, but this way is proactive. You poke and I can tell when it's happening. The other bit is like there's a little bit of spooky action at a distance with an explicit scheduler and an event loop and all those things that people think about when you think about like Node.js programs or asynchronous website stuff with callbacks.
Okay. And that to me just feels more like multi-threaded programming. Like you've got a bunch of threads all waiting on the same mutex isn't the right word. Like
effectively,
memory
it has that feel
or whatever.
Yes. Okay. Yeah, exactly. So someone's saying at least one of those browser add-ons is scooping up all my browsing data. Yes, I'm certain that all of them are. Right. So let's have a look here. What I've got is a memory, which really and this was me literally sketching 15 minutes one night before Jason and I talked. Mm-hmm. So it doesn't work particularly well. We have a memory class, which is modeling the memory. Now I realize I could probably make that a bus and have the memory just one of the things that are on the bus. And that way I can generalize and put other hardware on the bus. I load in an operating system, which is the OS ROM of a BBC Micro. Why not? I make a CPU and I give it the memory. And then this clock here is what I decided was like effectively the scheduler, the thing that's going to cause everything to tick in sequence. And it accepts a list of peripherals, of which there is exactly one, which is the CPU.
Okay, so what is a CPU.run inside of brackets? What is this?
So CPU.run is a function call.
Okay.
It returns, and because it's an asynchronous or a generator function, what it returns effectively is an iterator. So this is an iterator type thing, an iterable, a generator in Python. I'm trying to
hypothetically returning a coroutine in the C++ world.
Yes.
Okay.
Yes. And then in these brackets here, it's just an array. I'm making an array of these things so that I can potentially have multiple of them. So like if, for example, here I would do, video.run here as well. And then, like sound.run if I were to actually write all of those things, which I haven't got as far as doing.
Okay.
Timers.run. Critically, that's the other sort of really important part of any emulated system is like some source of time. And they could potentially, right. So that's as far as we got. And then what I'm doing here is I'm just saying like 10,000 times call clock.tick. And all clock.tick does, it's just to avoid scrolling, this is the clock.tick up here.
Uh-huh.
Oh, well, that's the first. And it's just literally going through each device and iterating on them, nexting them.
Nexting each? So
each.
Click, talk, no, tick, not...
Tick tock, you don't
tick,
stop.
Tick tock, clock, something, okay.
Something. It's what's now in the third hour-ish. No, 2 hours, 2 hours 17. So we're still making sense.
Hey, you know what? I've got an emoji bot here that says that the IDE is Sea Lion because that gets asked so often when I'm streaming. Your IDE is not Sea Lion, but it may as well be. This
is PyCharm, which is another JetBrains product. They make IntelliJ for Java and pretty much everything. They make PyCharm for Python. and they make Sea Lion, and I'm a big fan of their products. They're not perfect.
There's
Nothing
a Rust
is.
one as well.
Is there a Rust one now, or I wasn't sure that there was a Rust? There's definitely a Go one. I know you can get a Rust plugin for IntelliJ. This is the kind of problem. Like IntelliJ is their big overarching project, and you can get plugins for all of them which do the equivalent of most of the other languages. C line is different because C is just different enough. C and C++ are just different enough that they actually have a sort of different top leveling thing. C line could do Rust, yes. So someone is saying, yeah.
And
so there's a Rust plugin.
Your typing is about a 10-second lag relative to the voice when you're actually typing stuff.
Oh, useful to know. Thank you.
Yeah.
Okay, so we're doing next device. So let's go and have a look at the CPU. So I'm going to control click, which is something I taught.
You taught me how to do in C line, yeah.
Which is funny. So this is Python 3, and so I'm actually using type annotations. Viewers should be aware that these are nothing more than like subtle hints to the IDE and potentially something I could check with a linter. They don't materially change how Python works. Python is not a strongly typed language. This is me hoping to God that I can make it look at least as much like C++ as I can bear to get away with.
So if you actually passed in an int into this thing saying memory, Python would be like, sounds great.
Yep. It would be great. The IDE, on the other hand, would put little gray kind of like, are you sure you're meant to do this kind of thing? But maybe that's okay. So, yeah, it doesn't quite work as perfectly, but it's a useful step in the right direction. And it's certainly intention revealing to a caller without having to document, like in a doc string, what's going on. So I like it for that reason. The other thing I'm doing here is I'm declaring all the types of my member variables. In Python, everything is dynamic, so you can poke things in as and when you like. But it's nice to be able to lay them out. And I'm even using initializers here, which is subtly different from the way it works in C++. But this is not a Python podcast. It's not even a podcast.
I don't know what it is.
I don't know what this is. Is it vodcast? Vodcast? Vodka. Oh, there's a thought. Not yet. Okay, so the CPU is as simple as an A, an X, and a Y register, an S register, and a program counter. This handlers here is my way of implementing a switch statement because Python doesn't actually have a switch statement. You just have to have cascading if and elif and elif and elif and elif, and I just hate that. So it's going to be a list of function pointers. No, I don't want any gin. I'm being offered gin now by my 12-year-old. This is child services, please. Stay away. Yes, those are type annotations. Sorry, I'm being asked here. Yeah, and JSB to Python 3 is not going to happen. Python is too slow. So my handle list here.
It's a vodcast. Yes, it's a vodka cast. Yes. Sorry.
You're with me now. Yeah.
I'm looking at my messages here too. Someone commented last night that there would be less beer, but
we didn't rule it out.
We didn't rule it out. It depends on how late this goes.
Right.
Anyhow.
So we have all this state here, and this is pretty much all you need to do to model a CPU or a 6502. We've got the memory, we've got a flags thing, which is just an encapsulation for a few of the flag things because they're complicated, they're bit pattern stuff. We remember a bunch of stuff. The 6502 datasheet says, upon startup, the first thing that happens is it reads address FFFC and address FFFD, and that's what the program counter then gets initialized to. So that's what I'm doing here.
Also, the reset vector or something goes there by default, something like
effective. That. There isn't really a vector for that as such. I mean, the interrupt handler is somewhere else.
Okay.
And the NMI handler is now I'm unfortunately going to fluff on some things here that people are expert on and will remind me.
Sure.
But so I mentioned I showed you my little board the other day, the other hour, the other minute, whatever it was. And I mentioned Ben Eater and his channel. Definitely worthwhile watching the first few videos of that, because what he does is he plugs a 6502 on a breadboard and he just powers it, and he puts a clock that he can step himself manually, which he builds separately. And then he has an Arduino with like 16, I don't know where mine's got to, but like 16 wires off the Arduino, and he just plugs them around the 6502 as like the world's most low budget in-circuit emulator. Like, I'm going to just see what the chip's doing.
Okay.
And then he uses the Arduino program, and as he's single stepping the chip, he's going, what's happening? And you can see, like, the very first thing that happens is the address lines go to, there's a couple of cycles of nonsense, and then you see FFFC go over, on the bus, and the read go active, and then FFFD go active, and then you see it fetching from garbage, and you're like, oh, that's interesting. And so he hardwires the data pins to just be EA, I think.
Mm-hmm.
So it reads EA in the 2 cycles, and then you see the next thing it does is it jumps to the read address is EA. It's like, oh, I see, that's what's happening. And then it just forevermore goes EA, EAB, and it just says that EA is knob, if I remember right. It's just so cool, and it's like from first principles, like observing it on the outside with just cables. Super cool.
It's interesting comment that if you're reading these hardware specs or looking at schematics for, I think, any computer, even today, you're going to see that they recommend like a circuit, a timer circuit of some sort that holds the chip in reset for the first however many cycles while everything stabilizes, and then it releases the reset, and then you see it actually execute the code.
Right. And the way that you achieve that is with a NAF capacitor or a resistor type thing, and kind of like, oh, this holds it high for a bit longer, and then it gets pulled low, or something like that.
Yeah,
at least on a breadboard, on
right.
a breadboard style. So it's pretty cool. So it's really, really fun. Oh, say goodbye to some people. So that I initialize this handler array with like 256 copies of the self.unknown. So this is like essentially initializing my function pointer table for every instruction to be the unknown exception handler, an unknown instruction handler, which is rather than the 6502, which just plows on doing whatever it was internals told it to do. We actually stop.
Okay.
And then I poked in 4 instructions exactly, because those are the first 4 instructions that happen to be inside the operating system of a BBC Micro, and that is load A immediate, store A absolute, that SEI, the disable interrupts, and the CLD clear decimal. Okay. So let's go and have a look at this. So far, nothing interesting has happened, but this is my load A with an immediate. So the idea of this instruction is that it's 2 bytes long and 2 cycles long. The first cycle is it reading the fact that this is a load immediate. The second cycle is it reading the next byte and putting whatever that byte is into the accumulator and setting the flags, the 0 flag and the negative flag accordingly.
Yeah, the fact that all of your function and variable names start with an underscore is me as a C++ programmer primarily just hurting my brain.
Yes, no, this is Python's way of telling me this is private-ish. So this is sort of protected-ish. If you put 2 underscores in the front of a Python identifier, it is mangled, and not in a C++ mangled. It's meant to be, then the Python system rewrites it to be a different string so that in principle you can't see it and you can't guess what it is.
Okay.
In practice, of course, you can go and find out what it is. But that's like the very, very private. This is sort of the conventionally private, which is like if you see somebody calling the underscore version of a function from outside that class, the IDE typically kind of wiggles it and goes, he probably shouldn't be poking around in the innards of someone else's class. So that's what that is.
Convention.
Yes.
Okay.
If I put 2 underscores, it's more strong, but it's still get-aroundable. So here we can see that I say immediate value equals yield from self.readPC. And this is where we start getting into unfortunate hairy details, which I think would be actually quite interesting because we would still have these problems in C++. So this initially started up with me inlining this readPC.
Yeah, just remember if you scroll to wait a second to make sure everything touches.
Thank you. Yeah, okay, this should be stable for a while now.
Yeah.
So initially this load A immediate that I wrote out longhand was, im equals self.memory read byte yield self.pc plus equals 1. That was just written here on line 88.
Okay.
Because that's what the load A immediate instruction does, right? I need to read from the bus, which takes a cycle. So I have to yield at that point. And that's where I effectively am returning back out to my caller. And then when they resume, it resumes back with me. When they call next, I carry on at the next line.
Okay.
So that's how it was written. And that made a lot of sense to start with. And as soon as I wrote the second instruction, which needs to read also from the PC, and I made this function called read PC addr, which does 2 lots of read PC to read 2 bytes of the address, low byte and high byte. As soon as I wrote that, I thought, well, I need to make a function out of this. I'm just copy pasting the same bit of code. And now we hit the beginnings of the problem as I'm seeing it with the coroutine approach. And that is when you write a function, it is like a coroutine boundary. If I yield inside that function, this is a problem with the yield approach. That function now becomes a coroutine with my function.
Okay.
So load immediate here is calling a coroutine. Now, if the coroutine yields at all, it's yielding to me, and I don't want it to yield to me because I'm not interested in it yielding control back to me. I'm interested in its result.
Right.
So I have to transitively yield its yield out to my caller to say, no. If it yields, give control to my caller. Let them do whatever they're doing. And when they resume, you resume back through me to their coroutine.
So let's walk through this at the moment. You do this yield from self.readPC, so it jumps to readPC.
Correct.
It gets that byte of memory, and then it yields. And it yields back to LDA IMM.
Immediate. Which then immediately re-yields, because this yield from is a special version of a function call in Python.
Okay.
Yield from says delegate my yielding. Like if the thing that I call yields, yield it from me, like pass it through.
Uh-huh.
So the sort of the flow of execution will be LDA im is called, yield from self.readPC is called, goes into readPC, result equals self memory blunt. So far as synchronous, everything's synchronous.
Yeah.
Hits this yield. This yields to the caller. The caller is me here.
Yeah.
Oh, I then yield back out to the outer loop.
Because then, now one clock tick has occurred.
Exactly.
Okay.
When that resumes, when it calls next on me to get my next thing, my next result, you can see yield. This yield, by the way, is implicitly we could yield a value. We're choosing not to. It's yielding nothing because we don't have anything interesting to yield. We're just saying give up here. But you can, and commonly with generators, you yield a value. Right, for example, like a typical Python generator is like, hey, I'm a generator that takes another generator and I yield 2 times every value in that generator. So I just keep calling that previous generator and yield out 2 times the value.
Right.
Oh gosh, someone is saying fire's extinguished. My moderator is obviously doing something awesome. Thank you, Luca.
Oh yeah, sorry. I do have the Streamlabs bot in here, which just shuts down anyone that's.
Yeah, I have a very kind individual who is helping me out here, so I really appreciate what's going on. So yeah, and Richard also said NMI's reset vector is FFFC and FFFD, and then IRQ and break is FFFE and FFFF.
I think I'll take the break moment here to shout out to MVG, Modern Vintage Gamer, was on my 13-hour Doom stream and helped me quickly put out a bunch of fires also until I got the Streamlabs bot doing its thing.
Got it.
Helped
All right.
a ton.
So I think that the fires referred to here by my moderator are actually ones at his work. So he's put the fires out. So I'm glad. But for a minute, I thought, oh my gosh, am I being saved from some dreadful spam? But it seems not.
Okay.
So yes, you could be yielding a value. One could be yielding a value. We're choosing not to. So it's unimportant. The outer system doesn't care what we're yielding.
But this.
So yes.
I from my experience writing an emulator, immediately see one advantage to this approach. I know you're getting to the downside, that you self._PC plus equals 1. In my emulator, I'm constantly like, if someone needs to refer to the current program counter, I'm referring to PC -1 or PC +1 or whatever it needs to be, because the straightforward thing to do from a C++ programming logic is to increment the PC and then always refer to the last value or something like that.
Yeah, you can like the equivalent of self.PC++ in the read thing, and then now you have to account for it being
one ahead of where you're actually executing.
But interestingly, that oftentimes you'll see that things like when you push and pop the program counter on an actual CPU, it is already +1 or -1. You have, and like there's some accounting that the CPU has to do, or the operating system has to do when it's dealing with things like, well, I'm going to return to somewhere other than where I came from. I have to account for the fact that really the return address is like 2+ or the wrong place, because that's what the chip would do.
Well, and it makes sense that if you push, then the program counter would push to the next instruction, because then when you pop, you want to resume at the next instruction.
But making sense doesn't necessarily make sense.
Right. No.
For example, it's not free to increment a 16-bit value. It takes a clock cycle to increment a 16-bit value.
Okay.
The program counter is a 16-bit value. So when the program counter is incremented, sometimes could be pipelined while some other process is going on in the chip to save on a cycle at the end, where it's like, I've done all the things I needed to do with the program counter and now increment it. So a lot of the time, the increment of the program counter could happen within the instruction. And therefore, if you then push the value of the program counter, it may have already been incremented. You could reasonably see why, as someone who was implementing the CPU saying like, well, it doesn't really matter whether it's off by 1 or not, we just account for it. It's worth taking the hit in the software to deal with it than it is to have another cycle just to separately increment the program counter after you may or may not have access to program counter.
Right.
Particularly like ARM, where the program counter, at least in old money, the program counter was just another register as far as the instruction set tried to protect.
No, that's still true. It's
R15, it used to be.
Yeah, that's still true.
I don't know what it is in 64-bit mode nowadays. It's all changed. I remember when this was all fields.
It might just be W15 in 64-bit mode.
Whoa.
I'd have to check that out. Anyhow.
So yeah, we've got as far as like getting into the read PC. So this yield from is a subtlety that I didn't necessarily think I needed, but actually sort of cut to the chase of like, this is a disadvantage with doing the yield approach. An interesting observation here is that this read PC function has 2 values. And in fact, you can see the IDE has inferred what type it is. So that minus arrow, which is probably too small for you to see, it says that this function returns a generator of any int. Those 3 things are the yielded return type, the accepted type, which is something we won't go into here because it's too complicated, and then the function return type.
Okay.
So it has observed that there are 2 exit points of this function. One is the yield, which is implicitly yielding none, which is determined as any for whatever reason. And then here I'm returning an integer. And it knows that because I annotated read byte with an integer, so it's inferred this as being an integer, which means it knows that this is an integer. So there's some cleverness going on there. I mean, cleverness is relative, right? This is Python.
Commenter just said, by the way, that there is no access to the PC in ARM64.
Okay, there you go. Thank you. Cross channel. I should have brought up your chat on my screen. That would have been clever. I've got just enough room to squeeze another one here. No, it's still not too late. I don't want to cross the streams.
Killing your bandwidth. Yeah, you don't want to do that.
No, well, you can pop out the chat and then you can. So I actually popped out the chat and then closed the window on my side to get the chat alone over here.
Oh.
But anyway,
I'm not that smart.
Yeah, so there are 2 return values from here. One is the kind of like the yielded return value, which in this case is none, and that's the one that's passed through me in my yield from statement out to my caller, who then throws it away because it's just the next value of the clock. The clock did, device.next, and it didn't do anything with the return value. So that's that one. The second return value is that integer I'm actually returning, and that is the value of the yield from statement. So this im equals yield. Someone's saying thank you for being able to pop the chat out. Yes. This im equals yield from, this is the value of that return. And then I assign it to an im, and now I can do all the things I was going to do with it. Having got the result back, it's set zn here is, oh gosh, listen to me, set zn is the thing that's going to
You've spent too much time in America.
I have is making sure it's a 60 is an 8-bit value, and it's setting the z, which is the 0 flag, and the n for negative flag from the flags register, which we don't have to look at. It's not interesting. So here's a weird Pythonism. You might reasonably think, why the heck have I put this on 2 lines? Right. I'm a fan of giving a name to a variable if it wasn't abundantly obvious what that variable was doing, especially in compiled languages, because compiled languages will essentially take that away from you. There's no cost to making a name to a value. In an interpreted language, there's more cost, but it's sometimes worth the cost, or it's almost always worth the cost, right? However, there's a weirdness in the Python language means that this is a statement. Yield from is a statement, but the statement has a return value, and as a special case, you can assign it to a variable. If I use the IDE and say, hey, inline this, inline that local variable, it happily inlines it. But if I were to run this, oh, it's not doing it now. This happened to me twice. I'm going to try running the actual program. Oh no, I'm using the right keys. I realize everything's going to move around if I did it right. There it is. Yes. Look, syntax error. You probably can't see that because it's too small.
I see it.
But the IDE happily made a change to the code, which is not actually valid to Python. So I need to uninline that. So I had to put it on 2 lines, and that prevented me forever. I thought this was not possible in Python. As in, I thought this approach was doomed because of the yielding thing was going to cause me to have to write everything in one function. But thankfully not. So anyway, this is what a load A immediate could look like. You could just you call this function to get the next thing, you do the math, and then you yield because that took a cycle, and then it's the next instructions go, and that will flow around. And that's kind of pretty cool. I'm getting cycle perfection, but the side effect, the annoying thing here is that as a programmer, I thought this was going to save me, right? I thought this was going to allow me to write this without any kind of compromise. But now I have to know whether or not any of the internal functions I'm calling themselves yield.
Okay.
So that self.setZN on line 89 does not yield. Therefore, I do not have to do yield from. And it would, in fact, be an error to do yield from because it doesn't return a generator. It returns an actual value.
Okay.
This read PC does yield, and so it's a coroutine, or it's a task, or whatever the magical frame. So I know that I have to call it differently and deal with its results differently. And that's exactly the kind of thing I was trying to avoid. It would be just so nice to not have to do that.
Right.
And so this was a point where I think I was starting to despair in that evening, going like, maybe this is doomed to fail. Maybe this is the problem here. And so, like this works. If I undid it, didn't I? I'm just going to rerun the program, and it runs through, and there's a whole bunch of output here. And I'm going to stop scrolling in a second. But there's a ton of log output here. But it read A9, it read A's 40, it did a whole bunch of, it's working for the 4 instructions I've done before it throws an exception.
And the whole system is in lockstep. You know exactly how many ticks have occurred at any given moment.
Right. Obviously, there's not a motivating example of this because there isn't actually another device.
Right.
But the only other device is the clock itself, which is printing out tick on every single clock cycle, which you can see going tick, tick, tick. So it was enough for me to think, well, there's some legs to this idea. But when I sort of sat down and thought, well, how would I write this if I had, free reign? The yield is the wrong way round.
Okay.
I want to really be awaiting. What I want to do is at some point I want to say, look, suspend me here, and I don't care where in the call stack I am. So the yield effectively, the yield turns me into a coroutine, which means that anyone else who calls me has to know if I'm a coroutine or not. Mm-hmm. And then it eventually bubbles up through to the scheduler, which is the top of the chain, the thing that's calling next in this instance. And so I'm sort of doing a spooky temporary go-to on line 88 here, which is teleporting via, I'm scrolling again, I'm apologizing. The read PC call is teleporting via the call stack on line 88 out to the scheduler. And I've had to everywhere annotate that by saying yield from or yield. If we were able to turn it on its head and actually await instead and have await clock.tick or something like that, I wonder if that would obviate this, whether or not that would mean that I didn't have to mark the whole call chain as that, because at the point I do await clock.tick, I'm telling it what I want to, I'm sort of telling, I don't know. It's hard to get your head around this, and I don't know how to explain myself.
To pass the clock into each of the instruction calls, or make it a member variable or
member variable. So we go over to this one over here where I just copy pasted the code, and I don't know that I got it working, but I tried this kind of thing, and it starts, await clock here. It's probably slowly.
Can you embiggen that Windows? Oh, wait, is it a different size font than the other one was?
It is, because I did just change the individual.
Okay.
There you are. I embiggened it. Embiggened. It's a perfectly cromulent word.
It is a perfectly cromulent word. Both embiggen and cromulent are in the dictionary now because of The Simpsons.
I do know that now. So this is as far as I got, and I thought this was like maybe a different way of doing this, a wait clock, but I couldn't get it to work because everything now is a coroutine and it's marked as async. And I was trying to get my head around how that would actually manifest itself in the code. So this would ideally be where I say, hey, I inverted it, I turned it on its head, and the problem got easier, like sometimes these problems do. But I haven't got far enough down this world. So I got, in fact, you can see device dot What? I wasn't quite sure what I had to write there to make it work.
Can you go back to that while true await thing?
Yes.
So
Here.
okay, this is the run function. All right.
So this is the run function of the CPU. So effectively, this is much more like a thread, and it looks much more like a thread. So in fact, why don't we spitball, you and I, just the idea of how to achieve this in straight up regular threading. Because one way you could do this is to have one thread for every peripheral.
Yes.
And then have a mutex that each one of those threads is waiting on, and like a semaphore or whatever thing to say I'm finished. And then effectively their yield, the thing that which says their clock cycle, I would like you to wait for the next clock cycle. Really what happens is that they are relinquishing the one and only executing mutex, and then waiting on something to say ready to go for the next tick, something like this. I'm sure you can do it with a condition variable.
Yeah.
And then the outer, like the system or the clock, whatever you want to think of it, essentially in turn lets each one run, and then it blocks and waits until it's completed. And so then you're using operating system threads to do the suspend and resume for you. And of course, we all know that effectively, anytime I take out a mutex or I release a mutex, that's a potential for me to switch to another task. And that's a much more natural thing. I mean, it's become a natural way of thinking about the world. So I'm being asked if this is on GitHub. It is on GitHub, but it's a private repo right now because it was so dreadful. I'll open it up just so that we can have something to look at. I'm taking notes. I've done a terrible job of taking notes here. So, so instinctively, I could see a shape of a solution with familiar enough to me tools like semaphores and mutexes that you could puppeteer 6 threads, and some external process could guarantee that each thread runs until completion and then stops and blocks, and then you could run them in sequence one after another, and then that's one clock cycle, and then you go back to the first one and you lift up the gate, let it run for a cycle, and so on.
Yeah, and it seems like you should be able to do that with some sort of synchronization primitive.
Exactly. And at that point you think, well, okay, having got the shape of a solution that looks like that, can I drop in a co-await instead of the mutex, and then cooperatively pass the baton to the next process? Right. And I know how I could do it in assembly, right? This is the annoying thing, is like I know that that's effectively exactly what we're talking about with the Windows 3.1 event loop. This yield, anywhere there's a yield, would become an await, and that await is really a call the operating system to suspend me, store my stack and all my internal state and everything, and then unrestore someone else's thread as it happens the next peripheral, and call them until they do that, and then just round robin those things.
And doing that 4, 5, 6, 7 times per instruction sounds slow.
Right. It's not perfect. I think it's not, it's never going to be as good as we would otherwise like. But the interesting thing here is that when you call a function, and now we're going to talk about this like C style.
Right.
When I call a function to which I don't have, the compiler has no visibility, the compiler is having to make a call on what what global effects are visible or not visible. And so it's already having to be super defensive. Like if you're calling printf, right? Any variable that you had that was in a register has to have been written out to RAM, because presumably that printf call, or sorry, printf's a bad choice, like extern function, anything I did has to be visible. So I've already paid the cost by doing a function call, an unknown function call. But the converse of that is that only the registers that the ABI mandates have to be preserved and restored across function call boundaries are the ones that you have to preserve and restore as an operating system, a user mode operating system. So there's like only a few of them, right? If you know that, okay, the caller can scrobble EAX and EDX, whatever, and incidentally the return value comes in EAX, and as it happens that, I'm calling a function, the return value is a void function, so I don't even have to preserve EAX or do anything with it.
Right.
There's only a half dozen, it's not free, and it's an optimization barrier, but it's relatively straightforward. and this is the toy thing I did on my Risk OS thing, to just try and work out how this could be done. And it's relatively easy because the ABI gives you a kind of like a reduced set. So it's definitely not free.
Right.
But it is potentially not too expensive. And then if you can find a way to cooperate with the coroutine system of C++20, we already know that those, Gore's zero overhead, something talk.
Negative overhead, I think, actually might be the cost.
Negative overhead, yeah. There's a crowd pleaser. If the compiler can see through enough of that, then there is a chance that it can be even smarter and it can know what's going on and make some cross coroutine optimizations, which would be amazing.
Right.
I just don't know how to phrase it like that. And so now it's your turn to explain how coroutines work. Wah, wah.
Yeah, I can't do that. We tried
Thank you,
get
Richard.
the coroutine example running.
Someone's told me, just a comment on the yield from weirdness. You have to surround the yield from construct in an additional pair of parens to force it as an expression. Oh,
that makes sense, actually.
Today I learn. Okay, let me try that. Sorry to scroll around a whole bunch, but I'm just going to try. So now, funny thing is, PyCharm often, when I do an inline variable, it often puts an extra pair of parens around when I don't want it to. And if this time it bloody isn't. So, and then let's put another pair of parens around. No. No, that's because I'm a fool and I pressed. So there you go. Thank you, No. Are you? I wanted to ask No. Is this No from the children's TV program Ulysses? I would like to know. Did you have that over here?
No, I mean, not that I know of.
Okay.
Although I did, as a kid, spend a fair number of formative years living overseas, and some of the things that I saw was on BBC and Sky, and so I may get things confused sometimes as well.
I mean, I've lost track of where things come from. When people say, "Hey, what do you say in Britain?" I'm like, I don't know. I'd have to ask my mum now. Right. I've lost the ability to remember where things came from. Oh, I'm super pleased that yield from thing works. That's slightly less egregious to me. But it would be just so much nicer not to have to know that, and just know that wherever I am in my call stack, however deeply nested or not, I'm just saying this is the point where I'm going to want to pause everything and do the other thing, do the next cycle of some other device.
Right. Would you be ready for another break now?
I absolutely would, yes.
Okay, let's do another couple-minute break.
Okay. We'll do a short break, and then we should probably, we'll discuss how much longer we need to go and what we're going to do next and all those kind of bits and pieces, because, I mean, it's coming up for lunchtime here, and I could easily continue, but I want to make sure that, you're an hour behind.
I'm good for approximately 1 more hour, I think, which would put us at 4 hours if we take a break right now. Okay,
let's take a break then, and I might sit here for a bit longer and chat to myself.
Okay, I'll be back in just a moment.
You go. As my wife has already pointed out to me that she said, you're putting the you in YouTube, is what she said to me, because it seems to be only you talking. And Pantufel says, considering you never really actual CPU code, you could just call a function that does other work. Yes, that's essentially what we're talking about here. That's kind of it. I mean, in the context of C++, a compiled function, you need to do something. Otherwise, you end up with a nested call stack that never unwinds. So there's some kind of thing where you have to separate the call stack and let the other function have its own independent call stack and variables. Unless I misunderstand what you're saying there, Pantufel. But like the equivalent code is to write out longhand all of your local variables into a structure, much like a lambda, and then have a state machine that lets you kind of resume back in where you came from. I mean, Jason actually came up with some good analogies about using something a bit like Duff's device to remember where you are in a big state machine and go to back where you came from, which would allow you to kind of in each one of these points of yield would actually be an actual return. It would say remember to come back to line 90, return. And then the big switch statement goes, case 90, go to 90, that kind of feel. It's just that we would ideally like to use a language feature to do it, so we don't have to do something quite so error prone. Or I can sort of hear vague sounds in the background. There he is. So we can stop talking about him now. Oh, interesting. Another comment other than Jason is, oh, whoa, he's back.
Hey, all right.
Just been dissing you for the last 2 minutes, wondering if you'll ever watch this part of the stream.
Just for the record, that I drank my whole
good cafetiere or French press.
French press of.
I can translate. Yeah, another comment in my channel here is that in Kotlin, which is JetBrains' own JVM-based language,
Yes.
coroutine calls are transparent. No need for extra syntactic cruft.
There has to be. It makes me wonder if actually Go would be better at this.
It's Go routines, which are very high level abstraction. Yeah, I don't know about that. That's an interesting one because there's senders and receivers in Go routines, and I wonder how you'd end up like making sure everything was in lockstep.
Yeah,
that's the real trick. Go routines are supposed to be like you give things that they're like actors. I'm sure it is.
I got also a question on my channel I'd like to address. Do I plan to add coroutines to ChiScript?
Oh, golly.
I haven't actively maintained a ChiScript in well over 2 years at this point. So that's half of the answer. The other half of the answer is that the ChiScript call stack is actually the C++ call stack. So the only way without a complete rewrite of the way the system works would be to use C++ coroutines. So
Whoa.
I had been hypothetically waiting for years for this, but I don't think I'll ever get to that point. I would make no guarantees that I would.
That's interesting. So some other observations in my chat here, that Kotlin, there is a Kotlin native version as well. So Kotlin can compile to native, which is interesting. Pantiful talks about similar kind of operating system switching that we were talking about as well. And then I'm going to try and pronounce names. I'm sorry in advance. Magres de la Mancha says, I think you need to find stackful coroutines implementation for Python. I don't think it's possible with stackless coroutines. That is an interesting observation because I remember vaguely some kind of debate in the C++ world. Whoops. I'm just dropping things everywhere about whether coroutines should be stackful or stackless. And yes. I don't really remember how it went. So interesting. I don't know enough about it. But yeah, Go would be an interesting one. Yeah.
So coroutines in C++ require some level of type erasure and a dynamic allocation currently.
Mm-hmm.
And if you watch, in my understanding of which I think is correct, if you watch Gore's talks on this that show the coroutine being completely eliminated, it does rely on the compiler, as you said, having enough information to do heap elision to remove that dynamic allocation and then be able to inline the code and everything from there.
Right. Someone's just talking about a dynamic. Oh, now I've just fired up CLion, which is going to blow everything. Dynamic something emulator. Yeah, discrete event simulator. That's an interesting one. They are stackless in C++ 20. Yeah, that I was pretty sure, but I didn't want to say something where I'm supposed to know things. So thank you for.
And apparently Python is stack full. Someone states on my.
Oh, okay. That would. I wouldn't be too surprised. This is where it gets. So this is where I'm just sort of firing up CLion to show you as far as I got, trying to get this to work in C++, which is not very far, as is now playing to all to see.
Do you have I'm sorry. No, go ahead, please.
No, that was. I just thought I'd fire it up, if only so I could see if it lets me. Yeah, I can type. Okay, good. That's a start. We can try some trickery here just for the fun of it.
So
you were going to say.
Well, I'm going to start with not what I was planning to say, and now something else instead. Lines 1 and 2, I think, are extraordinarily important to note. Because C++ 20's coroutines are effectively useless without some sort of helper library. Right? Would you agree with that from what we've observed?
I agree.
Okay.
Yeah, it's almost like an STL for coroutines where like just the very bare bones parts, like, hey, we're giving you a vector. And you're like, a vector of what? He's like, I don't know, you put the thing in. It's your thing. You're like, well, hang on, the thing is not like an int or a float or something. Like the thing is like, something which models a promise, something which models a task. You're like, hang on, those are quite weighty things to not have an implementation of. You're like, yep, good luck, bye.
Good luck, yeah. So you, for listeners who are familiar with how structured bindings work in C++ 17, it requires a combination of implementation details and compiler magic to be able to destructure a value that's returned from a function. So you have to have type traits. You have to have type traits defined that say this is how many elements are in the destructured thing and what the types of those elements are. That's how tuple is implemented. It provides those type traits. Now, if it's a class with a bunch of public members, it doesn't have the same requirements. But this would be effectively like saying, yes, structured bindings work with tuple if you provide all of the type traits and all of the magic for us, instead of the standard library providing it for you. There is no standard library help for coroutines in C++20.
Which is an interesting decision. I mean, I can imagine, and again, I'm not involved in any of the C++ standards type stuff, but I could imagine that this was almost an affordance to the sheer panoply of possible solutions to the problem. And they're like, well, there are some parts of this which clearly have to have language support.
Right.
And there are parts of this which could, in principle, be written in user code, and they could be done one of 100 ways. So let's try and find a decent separation between those two sides. It put the part that can only be in the language, and then essentially punt. Don't make too many like set in stone decisions on the things which in principle could be generated by the user side of things, which is perhaps the right choice. So I was just updating my GCC in case it gets better.
Yeah, that, by the way, did cause a little bit of frame dropping-ish stuff here, but...
Oh, okay.
So, it is important to note that as of... What day is today? Today's Friday.
It is the 8th.
Yesterday?
May the 8th.
2 days ago. GCC 10.1 was officially released, which is the first stable version of GCC with coroutines.
Woohoo!
Which theoretically is the only compiler that supports coroutines as specified in the C++20 spec, I believe.
I will take your word for that.
I'm basing my word on CPP reference.
Complete aside, do we know who's behind CPP reference? You know, not everyone is a massive attention seeker like me, so they're not as known as being behind these type of things.
I don't know who started it, but it is a wiki, so it is updated by the community.
Right.
So I think there's been hundreds of people involved at this point.
I mean, that would make sense. It's a great resource. It is a great resource, and yeah.
So theoretically, this is what it looks like. You co-await. The CPU is waiting for each clock tick, and then it does things.
So this is my sketch, right? I'm going to undo these things, and I'm going to say, clock.tick.
You're getting
in fact, let's forget the numbers. We're going to do this. This is not going to compile. It's not going to work. Nothing. And so in this instance, I was modeling each of these as a task. So this is kind of relying on the stackfulness of it, which might be hiding to nothing, or I may be misunderstanding where the stackfulness comes in or does not. Oh, you got...
sorry, John Heed said Tim Song is the person who started CPP reference.
Oh, cool. Hey, John Heed. It's weird to say shout out onto someone else's YouTube channel from your own. That's the weirdest thing. I can see who your real friends are now, which is whose chat side they're on.
I'm assuming it's actually him because it's the PhD, but it could be someone who's masquerading.
Yeah, it could be anyone. All right. I doubt it, though. I'm sure they are the real Jean Heed. Okay, so this is what I was thinking. It's like, this kind of thing here. And then the problem, which is actually a good problem, I think, in this case, is that just like in the Python, where if I was to use the await version rather than the yield version, there's a sort of an appeal in the Python code to some event loop that has to be implemented so that it can schedule the events to happen. Now, as it happens in this instance, and this is perhaps a +1 the C++ approach, although again, so many details are unclear to me. But I really genuinely want to supply a very specific event loop of a sort to my coroutines and my awaitable tasks, because I want them to complete in a very specific order, one after another. There's no actual time passing, right? And it's not like there's an IO that's going to happen, raise a semaphore, some like event loop, some select thing is going to happen, and it's going to say, oh, you're now ready to run again. And then some dispatch routine goes, oh, okay, this is now provide the return value for this person who was co-awaiting some file. It's like, no, I'm literally running these back to back. And so being able to specialize the container and the promise type thing is probably an advantage here, because ideally this a clock here, which I don't know how to, I put sync wait here. I really don't want it to wait, because like if I put sync wait here, CPP Coro, which is an open source task.
Right. So I mentioned those includes, but didn't say what it was. So yeah, it's an open source helper for these things.
Right. But it's opinionated about the event loop. It runs an event loop effectively. It's there is a process by which it's doing this wait that has to interact with the operating system, because the assumption, quite reasonably, is that the only reason you would await anything is that some exogenous event is going to happen, like a network packet or whatever. So that like the root of this is some select loop that's going to dole out the return values to the right customers as they come in from the operating system.
Right.
And actually, someone's just put in my chat here that SimCPP is a discrete event simulation framework based on coroutines. And the interesting thing actually reminds me, a good friend of mine that I was chatting to like minutes before we started, there is an FPGA test library called in Python that uses coroutines exclusively to yield to kind of like, so you can write little device under test things that aren't in Verilog, they're in Python. And then you can sort of pump your circuit by yielding a few times and then checking the value of things. And that's how you write your tests. And I've forgotten what it is. I've written down Patrick stuff here because his name's Patrick, but I can't remember what the heck the actual library is called. Someone will put it in the chat. I'm fairly sure now. Someone will Google it faster than I.
Right. So, CLion doesn't have co-await and co-routine as co-return as keywords yet, it seems.
Correct. Yes, because you're right. So some things going on. Yeah,
hilarious. Well, hilarious to see the TV fall after that whole conversation.
That would be hilarious. I think I would see the funny side. Yeah. So CLion doesn't know about these keywords yet. That is true. I think CLion has mostly migrated away from their custom parser.
Right.
And they are now using Clang D for most things. It was the case that at the time they had at least 3 parsers. There was the Clang-based one. There was like the fast one that does, the simple brace matching style and understanding whether or not 2 left shifts are matching or not. Whether they're part of a template. You can imagine some fast and dirty regexe type feel. And then there was the one that actually understood everything that was used for autocomplete.
So I've now had 2 comments, and I don't know if they've been from the same person or not, but two comments on my chat side here that say, well, why not just emulate the hardware directly, VHDL?
Right. I mean, first of all, you can if you want to emulate that, but if you've ever run a Verilog Verilog simulator, that's back to it's only a fraction above the gate level, so the transistor level simulator we were talking about before. It's ridiculously slow. It's so slow. So that's problem 1. Problem 2 is the same problem we have with doing a transistor level simulations. We don't actually have the Verilog or the gates for everything that we would want to emulate.
But there are people have written their own 6502 Verilog cores that we could download, right?
Absolutely. Yeah, that's absolutely the case. But then you actually need an FPGA to run it on in order to get it to run in a timely fashion. And then it runs beautifully fast, super fast, as fast as you could possibly want, right? Like we saw, a 6502 is 3,500 transistors, not gates, 3,500 transistors. So there aren't that many things going on inside of it. So you could imagine on a modern FPGA, like one of these little things we were talking about last night, lattice jobby, you could probably fit 100 6502s and run them at like probably real time, if not faster, which is super cool. Right. But as to then run it on a general purpose CPU, they're just not good at running that kind of thing. I mean, what was the thing we were looking at last night, Jason? Sorry, just to give context to people who are listening.
We've mentioned last night several times. Yeah, my meetup met last night, and the speaker, Jeff, gave us an overview on VHDL FPGAs with C++. And the idea, the ultimate conclusion to his talk was you can design the hardware in VHDL and then use, do you remember the name of the program?
I can't even remember the name of the Python thing, which I'm annoyed at the moment.
Well, I know that Leslie is watching my stream, so if Leslie can pop that in here, because he was also in my meetup last night. It's a C++ tool that takes the VHDL, compiles it, transliterates it to C++, and then you can compile that as part of your C++ project and run the simulator in the C++ engine. Yeah.
Yes. Sorry.
Verilator is the
Verilator. That's right. Okay. And I'm gonna have to ask Pat what the heck that thing was called, because it's annoying the heck out of me now.
Wait, there's a GHDL here being brought up. I've never heard of that. Let's
thing. Okay. My offhand computer now being heard. Oh
open
no.
Source.
Some questions. C++ questions.
Apparently GHDL is the same thing as Verilator. Or similar. Verilator.
Interesting.
I'm going to get ventilators, I'm sure of it. Cycle accurate two-state synthesis. Okay, so I want to, if you don't mind, get back to your face. Where's your face? Oh, sorry.
Yeah, I can turn off. There's nothing interesting happening on my screen right now, and if I click
I was
right
just going to
button,
write on your screen. Oh.
There you go. You can write on my face now.
Yeah, but I have to bring you back. Hello?
Hello?
That's weird.
Oh, I thought you needed to test the mic.
No, it won't. After you killed your...
So the interesting point in the chat here from Luca was like, if you're running on hardware, you might as well run on an actual 6502 at that point. It's like, yeah, it's a good point, you know.
Oh, can you
there
see?
You go.
You
I
saw
can
that?
See that.
Okay. And I've heard before that this kills my thing. Okay.
Yeah.
I'm curious.
It kills even for me.
It kills your stream also. I mean your speed.
No, I can see your video encoding goes nuts at that point, and you become a strange person. So
I'm gonna go back to this. It's my incredibly complicated thing here that we've drawn many times. Now, this first of all, this is our square wave. This is our clock. This is so not realistic, right? An actual clock is like this on this hardware.
Watch the Ben Eater streams. He takes some clock signals and puts them through a real analog oscilloscope, and then he shows the impact of like the length of cables and why there are these random ass capacitors put across the board. He's like, yeah, just shove some capacitors in. And I've always thought, like, why is there sort of this like artistry to something which should be scientific? Why is it like, oh, maybe you need a cap here or that? And it's like, it's to try and like reduce that to make the bottom look more like the top. Although you have drawn them out of phase, confusingly.
Well, it was kind of an accident, but yeah, they are a bit out of phase. All right, so we've got, what was that issue that I linked you to the other day about the Commodore 64? So there's a particular scrolling technique that relies that it works on the Commodore 64. It was discovered really late in the life cycle of the Commodore 64. And it works on some CPUs and crashes on others. And if you go and read up on this or watch any of the videos on it, it comes down to so many different things. It's because of this instability in a clock cycle and how long it takes voltages to settle with each clock pulse and this kind of thing. You end up with the top 4 bits of certain banks of memory being unstable. No, top 2 bits of certain banks of memory being unstable. And therefore, you can't rely on those top 2 bits being anything reasonable while you're using this technique.
Right.
And it's just ridiculous. Right. And it's magic, right? So we have all kinds of questions. If you truly wanted cycle perfect, do you, is your clock tick on the rising edge? Is it on the falling edge?
Right.
Do you do anything in the middle?
Well, this is definitely even within my emulator. This is, maybe you're saying this to try and push a point that we talked about earlier, but like although there isn't a sequence in the hardware, one has to choose a sequence in which you tick the peripherals, right? In my case, I did, CPU, and then I was going to set video, and then sound, and then timers, and then whatever else. That's actually important if you're not doing all of the modeling that you're explaining there, because things like if the timer gets to 0 on a clock tick, when does it assert the IRQ pin? And does the CPU pick that up on the same clock cycle that it goes to 0, or is it on the subsequent clock tick?
Right.
And then you do have this thing where you might say, well, okay, the ordering is important. And so there are a couple of cases in JSB where things are done a particular way around, not because there's any rhyme or reason to it, but on a real machine, that's what would happen. And that may be because if there are 2 things going on at once, one of them is putting out more, it's a driving, from a transistor level, is driving harder than another thing, so that kind of overwhelms the signal, or it's just that the rising edge or the falling edge aspect to it. That's another thing that we've glossed over. Like for us, a cycle is like an up down, right? Or each one of those things that you've drawn there,
whatever they are.
But really, a cycle is an up and then a down, and those are 2 separate things. And so we could easily you could get closer to what you've drawn at the bottom, the wiggliness, by yielding at the rising edge and yielding again at the low edge, or awaiting high or awaiting low, or awaiting the next cycle.
Yield.
So
awaiting high, yeah, that's
because then that would kind of naturally fall out of the wash. Then if you had a system which went high, low, high, low, high, low, high, low, and then your await said what you're waiting for because you're modeling something. And at this point now, we're starting to write Verilog in C++, because that's almost exactly what you would write in an HDL is, at positive edge of clock, do this thing. At falling edge of clock, do this thing.
But I think it could still be an order of magnitude faster because you don't have to simulate all of the gates.
Right. Absolutely. Yes. And, the optimization opportunities across those things are much higher.
And if you...
yeah.
Oh, sorry. I just wanted to comment that if you read the hardware specs on these things, that your chips, whatever hardware chip you're looking at, will tell you if an event triggers on the rising edge or the falling edge.
Right.
Anyhow.
And I mean, but to your point, the kind of effect that you're talking about is sort of relying on some of the non-deterministic analog effects between the timings of things going on in the system, which is another level of simulation further on, even more so than I mean, I guess at our far left-hand side that we started this thing with, we talked about like the transistor level simulations, and that's nearer to that because inside those kinds of simulations, at least the one that Visual 6502 uses, think the potentials and models as like double precision numbers, and it's like pushing and pulling, and like, well, I'm driving this much current and I'm sinking this much current, and then where would the voltage be somewhere in between? So it is inherently an analog model of a what we think of as a discrete digital process. And I guess taking it an even step further, there must be, I'm certain, maybe someone will correct us on the stream, within hardware design companies, things that take it, simulators that go even further and take into account quantum effects, take into account RF effects and capacitance and inductance, because these are really big issues, especially when you're talking about like the nanoscale of modern processors, are not like these giant chunky things that you can see under a $300 microscope.
And those things like capacitance in the system would come into play with like this scrolling thing that I was just mentioning on the Commodore 64. That's why some systems could crash and some wouldn't, because it came down to the hardware.
Famously, in the hour before the BBC executives came to the Acorn offices to see this computer they'd hastily assembled, like literally over a 48-hour period over a weekend. It didn't work, and Sophie Wilson realized that you could put a wire in a particular place and like hold it in a particular area, and then it started working. And it was down to like inductance or capacitance or something, or like grounding, like some very analog effects. So like literally as it's dramatized, it's like as the execs are walking up the stairs, they're being stalled by Chris Curry, who's making, who's trying to like make, oh no, wait a second, look out the window, isn't it beautiful, kind of thing, while they're absolutely like kind of like tinkering with stuff, and eventually they get it to work, and the Acorn, the BBC Micro is born. But it's those kinds of things that we don't think about as digital engineers. And we touched on it again last night when we talked about like the RAM controllers that actually have to deal with the fact that as stuff gets warmer and colder inside you, on the side of a RAM chip, you have to adjust the delay lines so that the left-hand bit arrives at the same time as the right-hand bit, even though their track lengths are slightly different and the temperature affects how fast. It's a whole crazy world out there. We are lucky as software engineers that we basically get to treat everything as black or white, but there's a lot of gray area in between.
So where is the line drawn? If you wanted to make your ideal BBC Micro emulator, are you going to emulate clock ticks? Are you going to emulate rising and falling edge? Are you going to emulate the capacitance of the traces on the motherboard?
It comes back to the as-if rule,
right?
Which is a wonderful thing to be able to like draw on. If I can't write a reasonable program, or if I can't find a program of interest that is not overtly trying to subvert an emulator, if you're not trying to detect whether you're being emulated or not, if I can fool all of the canon of BBC games and all of the canon of like demos that have been written so far, that's actually good enough.
Okay. And what you do currently, does it meet that goal?
With the exception of the disk drive system, I think so. Can we increase the size of the video chats?
I can't, actually.
I mean, you're pretty much full screen.
On my side, whatever happened after you stopped your screen share, I no longer have the big U.
Oh, the big me. All right. If I turn off my camera and turn it back on again, this may either explode and cause this stream to end, or it fixes it. So I'm going to turn off my camera. 1 Mississippi, 2 Mississippi.
Hey, it did bring you
and
back.
I'm back. There you go.
Neat. Okay.
Hello, IT support. Have you tried turning it off and on again?
Pretty much.
We know. Yeah. Yeah, I can't increase my own face on this because of the way that we're doing it. If I right click on it, does it do anything? No,
I can't make my own face bigger. No.
And then there's a maximize button on the little thing, but I'm dread to touch too many things right now because we found something which hasn't exploded in flames.
This product is basically in beta, right?
Yeah. This is screen.so, which I think is largely given the thumbs up from me. Mm-hmm. I mean, not that we tried you typing into a window this time around, which we could give it a go.
No, I wasn't going to risk it.
Again, we're the sort of like don't poke the bear part. So yeah, I think I'm largely there now. My friend who wrote the JIT version, I think his emulator is he actually has done a whole bunch of changes to JSB, but that's kind of one of his things that he hacked on to get a bit more context about some of the more subtle edge cases of things. But his JIT, I think, is his emulator Beeb JIT is probably more accurate still. There are probably a little one or two things in the video emulation that we probably need to fix up on, but that's the one that we don't have like a go-to implementation to check against. So I used to use Visual 6502 to check like which clock cycle things happened on.
Right.
And with the exception of that cycle stretching thing where the 1 megahertz and the 2 megahertz buses were kind of lined up, then everything else was perfect on Visual 6502. The video circuitry, we don't have that. And unfortunately, my BBC Micro is in my loft in the UK and has been for a decade now. And I should really get hold of it. But it means I have to rely on other people running experiments and timing-based things and, typing in programs and taking photographs of TV sets and then sending me back photographs of like, this thing took this long and this thing took that long. And I'm like, make sure that my code does the same. The nice thing about an emulator is that you can take those observations and you can write a unit test. So I have a unit test for every cycle, and I have any game or protection system or thing that was particularly sensitive to the way the world's set up, I would turn into I guess more of an integration test.
Okay.
And run it as part of the pre-commit. So I'd then be pretty sure that I hadn't accidentally buggered something up by switching around a couple of lines that otherwise were equivalents. Like Alien 8 still decodes and Lunar Jetman still decodes, right? The games aren't checked in, and I got permission from Kevin to actually put his protection systems only into my code, but not the actual game itself.
That's funny.
It is, yeah.
So
the only thing I was trying to get out of this was, is there a way to write the code in C++ rather than JavaScript, where I'm sort of code genning?
Right.
Is there a way to write this in C++ that's more easy to write, I suppose? And it seemed like coroutines were a way of doing this, and there was something I didn't know much about.
But at the moment, it seems like you haven't quite figured it out.
I haven't quite, no.
I got one comment here who said, asked if you had checked out Mr. FPGA BBC Micro implementation.
I think I looked at it a long while ago, and I think it's I don't remember whether it passes all of the egregious tests. But it certainly has the potential to do it in a much more principled way.
Right.
Maybe that's it. Maybe it's just the language is wrong, right? In a funny sort of way, the JavaScript taking the disassembly tables and generating JavaScript from it is me writing a language which is perfect for expressing what each instruction does. And you could say, well, if you're going that far, why the heck not just write something else that is like the perfect emulation language and have it so that it code gens the perfect code.
And maybe that makes sense. I mean, and then we're kind of almost come full circle to like Verilog or something. It's just a higher level thing.
Right. Yeah. I mean, that's an interesting point. And then to try and keep it grounded in some C++, this is, down the line, some kind of herb magic generative programming approach could even be used to say, like, okay, I can annotate the functions in the right way. Maybe I can rewrite them as we go to yield, or whatever yielding really is in our world, at the right point, and make it still ergonomic as a programmer to write in a pretty clear, fairly straightforward C++ way, and yet have the system do the right thing in the right place.
So what do you, I know I brought this up privately earlier, but what do you think about an approach like Duff's device or something that is a switch statement that jumps into where you last left off? So
when you popped for the break a moment ago, I was thinking out loud a little bit about that, and that's basically that would be great, but I think it detracts. So like as soon as you're using something like Duff's device, which is a big, for those aren't sure about it, and I'm going to give my interpretation of what it is essentially like a big switch statement with labels that you can go to within them, and a for loop can be outside that, or a while loop. And there's some sort of trickery to be able to basically resume back in. Resume is strong, but effectively you still need to have a way of knowing where to come back to.
Yeah.
So at each point where you could end, you need to have either a label or a switch statement, a case statement, which is essentially a label, just under a different name. And you need to be able to store that somewhere. And of course, there are GCC extensions to allow you to actually have computed go-tos where you can store the address of the label in a variable and come back to it through that way. Otherwise, you have to just have a process like a macro or something, which is going to assign you like a unique label name at that point, so that you can say, come back here.
Right.
And also, if you're using any kind of go-to type thing, you're going to lose out on all of the internal state. You can't have a local variable anymore, because when you come back to it, the local variable will be uninitialized. It will be a different variable, unless you can preserve it.
Make them all static.
Yeah, I mean, that works until you need to have two of them. So you could have like 2 CPUs.
Oh, no, yeah, you could not have 2. Make them all thread local. It'll be fine. Run each CPU in a thread.
There you go. Yeah. Or, access everything. They have to all be member variables, which is effectively at that point we're starting to sort of reinvent something which looks not a million miles away from either lambdas,
right,
or what must be happening under the hood in coroutines.
Yeah, just a resumable lambda. Be. You want a resumable lambda.
Which is to say a coroutine, right? That's what a resumable function is, just a special case of that. And then the coroutine, through some mechanism, is storing those local variables in a place that you can't get at.
Right.
So that when you come back, in I is still the 12 that it was before you ran. Yeah, I think it's not clear to me. It's not clear to me at all.
I'm very curious if, and I don't see a way forward. Like my imagination does not see a way forward. But if there would be some sort of templatey, context-free foo that we could use to generate these things for us.
Right. And that sort of speaks to the generative thing a bit. And I also wondered whether or not, there's some crazy template trickery that one can do to like at least make a sort of DSL, for want of a better word, for each instruction.
Yeah.
You could imagine me saying instruction of, and then passing in, well, I read on clock 3 and I write on clock 7. And that's how I kind of like write what is my at the moment is a table is an ASCII string for each opcode, and I parse out the ASCII string and kind of work out what needs to do, and there's a bit of extra annotation. You could instantiate one of those things and have that be and if it was context expert enough, the compiler was smart enough, then potentially you could unwind all the code and make it all lovely. I mean, maybe there's a way of doing it that way.
Is there?
I can't quite see it, and I'm no template expert.
I'm wondering about, and I don't know if we have anyone on the chat who could listen to this, and at this point we're just pontificating or something, but mutually recursive functions. What happens if you actually write it so that the next tick calls the last thing, which calls...
Right.
And
right. I mean, that lays bare the structure of what you're trying to achieve in a way.
Yeah.
But the trick there is that each call that you do, as you say, is nesting further.
Yeah.
But also each call starts at the top again. And actually, you don't necessarily want that, because when you call, the CPU calls the video, calls the whatever, calls the other, what calls the other.
Yeah.
Now, if you made that end, so that was like one cycle, maybe that would work, and it returned all the way back up to you. But then
that might work.
You carry on executing.
That might work.
And at that point, essentially, in essence, that is what JSBeeb is doing right now.
Okay.
Because it just says, time passed 7, and it just so happens that, again, this is the CPU is primary. The CPU is told to run for a certain number of cycles, and it's essentially implicitly it runs all of the other peripherals. It just so happens that the CPU is the only one that has any kind of useful state that would be a pain in the ass to extract and make separate.
Right.
Everything else is either a sound chip, and it's like I have my 3 registers, and every tick I just look at the 3 registers and do the things that says to do next, and then I'm done. Mm-hmm. Or it's the video chip, which is broadly the same.
Right.
Or and so there's no state that they need to keep in, like, there's no really there's not a multi-cycle state that they need to keep track of that's not already mandated by their design and visible to the outside world.
Yeah, so if you could rely on that, then that would work. Have the CPU just call all the other devices on each clock tick. That's effectively it's exactly what JSBeeb is doing now, and that's not so bad. So where that starts to fall down, the only thing I can think of, and this is actually visible, and this is not something I've cared about too much in JSBeeb, is that you can have a coprocessor in a BBC Micro, right?
And now you've got 2. Exactly. Now you've got 2 CPUs, and you're like, well, there's kind of who's the first among the equals here. And as it happens, obviously the actual CPU that's in the motherboard is the one that's driving the show, but usually the coprocessor is much faster and is off doing other stuff. So actually what my implementation does is like, okay, one tick of the 6502 on the main board is like 10 ticks of the faster thing. And it's also a 6502 or it's a 65C12 or whatever. It's not actually the right CPU. It's a very sketched implementation. So and luckily no one really, there's one exception, is taking too much advantage of the fact that there is cycle perfection between these two things. Like there's necessarily on the other end of it, almost like a serial cable, right? Hey, I'm communicating. There's a protocol that I'm communicating with the other program running on the other CPU, and we've agreed on this kind of stuff. And it's really hard to schedule. So like, there's a lot of slack in the implementation that we can take advantage of. The counter is unfortunately the master version of Elite, which doesn't work very well on my emulator because there is a lot more lockstep stuff going on between the two CPUs, as far as I can tell. I haven't really looked at it. Yeah, someone's saying that model it with a clock being a generator yields an array of promises, and each promise is an operation that happens. Yes, that's sort of what we're trying to do, and maybe that's just what I'm not achieving because I'm just unable to find the right way to phrase it and to have everything look ergonomic without filling the code with yield froms and things. But
maybe that's just what we have to do. Yeah,
maybe that's it.
I don't know.
So yeah, I don't know. The promises thing maybe is, or the generating coroutine thing is probably a bridge too far, I think, is what I'm sort of putting out from this, and that most of the time the CPU is just fine, and maybe main is already doing it this way because maybe that there's not the same level of accuracy needed by main, or maybe it is just ticking everything and it's just written out and it's like someone just bit the bullet and went, okay, well, every time the CPUs tick, I have to look at where I am inside instruction 7, step 3. Okay, let's do that. Because the reason I say that is because most arcade machines that it's emulating have multiple CPUs and multiple sound chips, multiple video chips, and they're all like working in concert. So I can only imagine that it's a much more difficult problem for them. So I don't think we've really covered the coroutine aspect here, but I'm wondering if we should wind at this point here, unless there was some other aspect that you had. This seems like a natural place, and I'm running out of a little bit out of steam myself.
Yeah, you haven't had lunch yet. I haven't had lunch yet. Yeah,
it's about that time, isn't it? So we haven't really done any programming.
What's that?
We haven't done really any programming. I showed Python for God's sake. So
we didn't promise to do any programming. We said we will talk about it.
That is true. I think we've made good on that promise. We definitely have covered a lot of ground in terms of like the kind of emulators from the 1980s era hardware, early 80s hardware. There's been a bit of conjecture about some of the other higher level emulation techniques that we've talked about. You mentioned the Dolphin emulator. There's been some other things in the chat.
I will say out here for people who are curious, the Dolphin emulator team has a blog, and they occasionally post articles about these things that they are doing, and it is just mind-blowing stuff.
Right. Yeah, there's some very cool things being done out there, all in the name of emulating GameCube hardware.
On the name of being able to play games from 30 years ago or whatever.
Oh, it hurts that's true. In my mind, I'm thinking that's not 30 years ago, but no, it is.
GameCube's not that old, is it?
No, let's think. It's probably 20 years old, isn't it?
It's over 20.
Yeah,
anyhow.
I was working at Argonaut when I got my GameCube. Oh gosh. Anyway, right. I think we are going to. Sorry, I'm being gestured by my son, who's asking questions about things he can or cannot do. So, all right.
So if either one of us has some breakthrough in how this works in C++, or if someone mentions to us,
yes, then we should do this again and talk about it.
We'll reconvene. Yes.
And then maybe we'll do this again some other time anyway. I think that this is just one of the many things that we have in common that we've discovered over the years, that we like playing around with old hardware and tinkering with it, and even emulating it. So maybe there'll be another topic sometime, but we'll have to see about how that works out. And being locked in our houses all day every day certainly helps the creative juices flow a bit.
All right. Awesome.
Cool. All right. Well, I've realized that this computer over here is now locked, so I'm gonna have to shift over here before you can
end your stream.
Yeah. So I'm stuck streaming forever if we're not careful. Because I alt-tabbed away, or rather, I was alt-tabbed away by somebody. Yes,
Are you
yes.
back on the same screen?
You did not. Oh no, that's true. Coco TB. Thank you, Patrick. Okay, Coco TB is the name of the Python library stroke simulation thing that uses yields in much the way that we were talking about earlier.
Okay.
GameCube is 18 to 19 years old. Thank you, Inverse Phase. Yes, and just another reminder, anyone who's watching this who's enjoyed what we've been talking about, check out Inverse Phase's music and his live streams about playing old video games as well. I feel compelled. It's good fun to watch him and listen to his music. So all right, now I feel like it's a product placement hat. Mates, shout outs is what that is. And thank you to Luca for being the moderator on my side.
And
for
mugs
joining
are
us.
available on Matt's website.
Yes, and if you while we're here, you can now the new thing. If you're a Patreon, I will, and you subscribe to a certain level that I forget, I will send you this thick piece of paper with a Compiler Explorer logo on, which is apparently a coaster, and also I have fridge magnets. Oh, it's exciting! There's so much swag.
You gave me a limited number of those fridge magnets, and I've been very careful with them. And I handed them out to some students at one class. I'm like, I've only had 3 of these, so if you want one, right? And I give them out, and then I noticed that one of the guys in the front row who has one is sitting there, and he's been like folding it back and forth the whole time. I'm like,
I realized that I hadn't like fully accounted. I send off orders for the things, and at the time when I placed the order for all this stuff, it's a lot of cash, right? It's hundreds of dollars worth of stuff.
Yeah.
I was going to say crap then, but but and you're like, oh gosh, my golly, that's a lot. And then I kind of have to account for it in the Patreon like stuff, which is all great because and then when I'm giving them out, that's lost. The association with how much it costs is lost. And so I have literally no idea. So I had to get a spreadsheet out the other day and go, when I send somebody something in the mail for them, how much is it costing me? And am I actually net up or net down on this one? And I'm about neutral, which is fine.
Yeah. All right.
So, okay. Well, thank you everyone for joining us both. We may do this again.
Thank you,
We
Matt.
may not. We'll see. Thank you, Jason. This has been a lot of fun. And you missed this as well. While you were out, my wife said to me, you're putting the you in YouTube. She said, it's only been you that's talking. And I'm like, no, he was talking to, I'm sure. But she's probably right because that's what I do. So I appreciate your being my foil. And I guess we should say goodbye.
All right. Goodbye, everyone.
All right, my friend. Bye, everyone. Thank you for watching. Don't forget to like and subscribe. Are we not supposed to say that?
Yes, like and subscribe.